Right now, the solar system is being shot through by a storm of invisible particles, shrapnel from dead stars, while a silent gravitational current drags us, all of us, around the Milky Way. If space is empty, why does it feel like we're moving through an unseen ocean? And what's really above us and below? Look up at night and you see calm, steady light, yet the sky is stitched with forces that never sleep. Our entire neighbourhood is threaded through layers we cannot see but can measure. In space, above and below are not directions you can point to with a compass. They are choices, reference frames we build to make sense of motion, pressure, and the shape of a galaxy. For the solar system, that frame is the Milky Way's disk, an immense rotating plane with a north and south. Once you adopt that geometry, vertical stops being poetic and becomes physical, because different heights mean different environments. At one altitude, dust and cold gas crowd together, hiding stars and birthing new ones in darkness. At another, the material thins into ionized haze, then into a hot, rarefied halo where magnetic fields and plasma behave like weather, and through every layer, signals arrive carrying news from places we will never visit. Some travel straight and fast, indifferent to magnetic fields. Others spiral, scatter, and forget where they came from. If you want to know what exists above and below the solar system, you cannot simply look. You have to learn how to read the sky the way you read an ocean, by its currents, its turbulence, and the faint pressure it exerts on everything passing through. This documentary follows that reading from the smallest boundary that shields us to the larger structures that steer us. We will watch the solar system move inside a protective bubble that is not smooth, not sealed, and not constant. Its edge is a living interface. Beyond it lies our local cavity in the galaxy, carved and reshaped by ancient violence, still echoing in the chemistry of nearby space. Farther out, the Milky Way reveals itself as a stacked architecture with chimneys, fountains, and a halo that is more like an atmosphere than a void. Then the story turns upward into the high-energy sky, where the most extreme events advertise themselves in light our eyes cannot register. You will see how instruments reconstruct that invisible spectrum, and why the brightest truths often arrive indirectly. And the story turns downward into gravity, quiet, patient, and absolute. The solar system's path is not a simple loop but a three-dimensional drift. Guided by mass we can map only through its pull. As the scale widens, above and below become less about the galaxy and more about the universe's flow. Whole groups of galaxies ride along filaments toward deeper basins, and our motion becomes a measurable vector against relic backgrounds that fill every direction. By the end, the question will look different, not because it is answered too easily, but because the terms themselves evolve. Above and below resolve into a layered atlas of radiation fields, magnetized plasma, and gravitational structure, stacked like invisible weather systems around a moving ship. There is no emptiness here, only unfamiliar substance, and once you learn the language of those layers, the sky stops being a backdrop and becomes a map. Tonight we begin building that map, from the plane of the Milky Way to the borders of our local space to the forces that decide what can reach us. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We will climb from the solar system's immediate boundaries to the Milky Way's vertical layers, then outward to the cosmic web's quiet geometry. Along the way, each chapter sharpens the same mystery until up and down become a measurable landscape. We learn early that space has no true up or down, because there is no preferred direction built into the vacuum itself. Yet every spacecraft still needs a frame for navigation, and every map needs a north that everyone can agree on. The misunderstanding starts with language that feels harmless, because our brains are trained on horizons and gravity. We say above the solar system and below it, as if the universe has floors, ceilings, and a fixed orientation. On Earth, up is defined by gravity and the ground beneath our feet, so the word carries emotional weight. In orbit, astronauts can flip end over end and still feel normal, because their bodies are in free fall. In deep space, direction is only relationship, and relationship depends on what you choose to reference. Up is whatever you decide, until a larger structure makes some choices practical, repeatable, and useful across generations. Our larger structure is the Milky Way, And it is not a vague idea in a textbook illustration. It is a rotating disk of stars, gas, dust, and magnetic fields, with a thicker halo around it that extends far beyond the bright band we see. When you look at the night sky from a dark place, the Milky Way appears as a pale river of light. That glow is not a cloud around us. It is the edge-on view of our disk, packed with distant stars and dimmed by dust. That disk gives us a meaningful horizon, because it is a real physical plane with measurable thickness. Astronomers call it the Galactic plane, and it becomes the reference for vertical in a way that is both geometric and dynamical. From that plane, we define a north and south that can be written into catalogues and software. The North Galactic pole points perpendicular to the disk, and the South Pole points the opposite way, like arrows drawn through a spinning vinyl record. This is not cosmic absolute truth, and it does not claim to be. It is a coordinate system tied to the galaxy's geometry, and it works because the disk is real, rotating, and gravitationally dominant where we live. Historically, this was not always obvious, because the Milky Way's structure was hidden behind dust and distance. Early star counts hinted at a flattened system, but only later surveys and radio observations revealed how the disk continues through obscured regions. The solar system is not centered in this structure, and that fact quietly shapes everything we measure. The Sun sits about 8 kiloparsecs from the galactic center, deep in the outer disk where the stellar density is lower than in the crowded inner regions. 8 kiloparsecs is about 26,000 light-years, a number that is easy to say and hard to picture. Light would need 26 millennia to cross that gap, while the Sun completes a galactic orbit on a timescale of hundreds of millions of years. That distance matters because the galaxy's forces change with radius, and rotation is not like a solid wheel. The speed of stars around the center stays surprisingly high far out, a clue that much of the mass is not in the visible disk. We also are not exactly on the midplane, which is the disk's densest layer. The Sun is slightly offset, close enough to forget in casual speech, yet far enough to measure with precise star positions and dust distributions. The midplane is where gas clouds concentrate, where stars form, and where gravity is steepest over short vertical distances. It is also where dust is thickest, turning the plane into a luminous band that is beautiful in photographs and frustrating for optical astronomy. To talk about above and below, astronomers use galactic longitude and latitude, a sky-based grid that wraps around us. Longitude runs around the plane, and latitude measures angle away from it, giving every direction a clear address. Latitude is our vertical dial, and it is a simple idea with powerful consequences. At 0 degrees we look along the plane, and at 90 degrees we look straight out of the disk toward the poles of our galactic coordinate system. This frame is practical because the disk is thin compared to its width, even though thin is relative. The Milky Way spans tens of thousands of light-years across, but only a fraction as thick where most of its stars and cold gas reside. Thin does not mean simple, and the disk is not a single uniform sheet. The disk has layers, from cold molecular gas near the midplane to warmer ionized gas above it, with turbulence and magnetic pressure helping hold those layers up. In visual terms, imagine a glowing city seen from an airplane at night, with fog and smoke trapped near the streets. The midplane is the crowded downtown, while higher latitudes are like clearer air, still filled with faint haze but less opaque. Above the disk, the halo extends farther than the visible stars, and it is easy to underestimate because it is dim. It holds hot plasma, magnetic fields, and a large share of the galaxy's dark matter, shaping orbits even where starlight thins out. So the paradox resolves into a better question. If up and down are relative, what exactly fills the directions perpendicular to our galactic home, and how does that vertical structure change what reaches the solar system? The answer matters because the solar system moves through this layered environment, and motion turns geometry into history. We are not drifting in a void, and the galaxy is not a static backdrop, because its gas flows, its fields ripple, and its mass distribution evolves. The Sun orbits the galactic center, but it also bobs like a horse on a slow carousel. Over tens of millions of years, it oscillates above and below the midplane, crossing the densest layer and then climbing back toward thinner regions. This vertical motion is not speculation, and it is not based on a single measurement. It is inferred from stellar kinematics and the gravitational pull of the disk's mass, using the way nearby stars share similar vertical speeds and restoring forces. In plain terms, the disk's gravity acts like a spring near the midplane, pulling objects back toward the densest layer. the exact period and amplitude of the sun's bobbing encode how mass is distributed, both the mass we see and the mass we can only infer. The oscillation tells us the disk has structure, because structure changes the pull. A smooth disk would tug differently than a clumpy one, and the sun's path records that difference in the statistics of stellar motions around us. Every crossing of the midplane changes our neighbourhood, even if the change is gradual rather than dramatic. The density of gas, dust and star-forming regions rises near the plane and falls away at higher latitude, altering what the heliosphere encounters. That change can alter the radiation and particle environment, because denser regions host more shocks, more massive stars, and more supernova remnants. It can also change the probability of close encounters with massive clouds, which can perturb comets and reshape local interstellar conditions. Two threads will guide this documentary, and both are tied to the vertical axis we have defined. One thread comes from above and below as radiation and particles arriving from high galactic latitudes, where the line of sight exits the dusty plane more quickly. Cosmic rays are part of that rain, and they are not a gentle drizzle. They are charged particles, mostly protons, plus heavier nuclei and electrons, accelerated by shocks, supernova remnants, and other violent engines that convert bulk motion into particle energy. Because they are charged, magnetic fields bend their paths, and the bending is rarely simple. The galaxy's field has ordered components and turbulent eddies, so cosmic rays scatter and diffuse, arriving at Earth from directions that often hide their true origins. That scrambling hides their sources, but it does not erase their energy or their effects on matter. When cosmic rays strike an atmosphere, they generate cascades of secondary particles, a shower that can be measured at the ground, and that subtly contributes to radiation dose. Gamma rays add another clue, and they behave differently because they carry no electric charge. They travel straight, and they trace interactions between cosmic rays, gas, and radiation fields across the galaxy, lighting up regions where high-energy particles collide with interstellar material. In the plane, gamma-ray emission can be bright but confusing because there is so much gas and so many overlapping sources. At high latitudes, the view can be cleaner, yet the faint glow that remains becomes a map of the halo, the local bubble, and distant backgrounds. At the highest latitudes, the sky carries an extragalactic background that is easy to overlook. It is a faint glow from countless distant sources beyond the Milky Way, blended together by distance, redshift, and the limits of our instruments. Some of the most energetic messengers may not be photons at all, and that is where the story becomes stranger. Neutrinos pass through matter with little interaction, carrying information from extreme environments, because they can escape dense regions that trap light. The other thread is gravity and mass beneath us in the disk, and beneath here has a precise meaning. Beneath means toward the mid-plane, where mass density climbs and orbits are shaped, and where small differences in density can accumulate into long-term dynamical effects. Molecular clouds dominate the cold mass in the disk, and they are not smooth blobs. They are huge, structured, and capable of perturbing stellar motions over time, with filaments, cores, and turbulent flows that can span tens to hundreds of light years. In visuals, these clouds appear as dark lanes against star fields, or as glowing shapes in infrared and radio maps. They are nurseries and obstacles at once, places where new stars ignite, and also places where dust hides the very starlight we want to measure. Spiral structure also matters, even though it can mislead the imagination. Spiral arms are not rigid objects, but patterns that concentrate gas and trigger star formation as material flows through, compressing clouds and setting off chains of stellar birth. The sun's orbit threads these patterns, and the timing is part of the mystery. Over long time scales, the solar system can drift relative to arms, changing nearby supernova rates and cloud encounters, and shifting the background radiation field that surrounds the heliosphere. Then there is the dark matter halo, the mass we cannot see directly but cannot ignore. It is not beneath or above in the everyday sense, but it envelopes the disk and sets much of the gravitational potential that keeps the galaxy rotating as it does. The halo's shape and density affect the sun's motion, including the vertical oscillation we described. They also influence how the disk warps, flares, and responds to satellite galaxies, leaving signatures like ripples in star counts and bends in the outer gas layer. All of this creates tension with our intuition, because the word space suggests emptiness. We imagine empty space, Yet the solar system moves through an unseen ocean of fields and particles, where even very low densities matter over astronomical distances. Magnetic fields thread the disk and halo, and they are more than lines on a diagram. They guide charged particles, store energy, and couple distant regions through waves and turbulence, shaping how cosmic rays propagate and how gas clouds resist collapse. Hot plasma fills cavities carved by stellar winds and supernovae, forming bubbles and chimneys that can vent material upward. Dust grains drift and align, absorbing light and re-emitting it in infrared, and their alignment lets us infer magnetic directions through polarization. Much of the mass is invisible directly, and that invisibility is a central challenge rather than a footnote. We infer it from how stars move, how gas rotates, and how light bends and scatters, building a gravitational map from indirect but consistent evidence. So above and below become investigative directions, not metaphors for height in the universe. They are about gradients in density, radiation, and gravity, and about how those gradients change as we move through the galaxy's layered architecture. To investigate, we need maps that cover the whole sky, because the vertical axis is a global feature. We also need time, because motion reveals what images alone cannot, and because the galaxy's structure is written into velocities as well as positions. Gaia provides the backbone for motion, and it does so with extraordinary precision. It measures positions and velocities for more than 1 billion stars, letting us model the galaxy's gravitational field and detect subtle patterns in how the disk breathes and bends. With Gaia, the disk becomes a dynamical object rather than a static backdrop. We can see streams, ripples, and vertical waves that hint at past encounters and hidden mass, including the lingering gravitational fingerprints of satellites that pass too close. Planck maps the sky in microwave and submillimeter light, where cold dust becomes visible instead of obstructive. It traces cold dust and reveals magnetic field orientation through polarized emission, turning faint alignment signals into a galaxy-scale compass. Fermi surveys the gamma-ray sky, and its maps feel almost like weather charts for high-energy processes. It shows bright sources, diffuse glow, and large-scale structures that reach above and below the plane, hinting at energetic events that pushed particles into the halo. Cosmic ray detectors sample the local particle rain, which is only a tiny piece of a much larger circulation. They measure energy spectra and composition, helping identify acceleration mechanisms and propagation through magnetic fields, while also revealing how the sun modulates lower energy particles. Neutrino observatories add a rarer channel, and rarity is part of their drama. They watch for faint flashes in ice or water, looking for directions and energies that point to extreme sources, and they do it while most neutrinos pass through Earth as if it were glass. Each tool has limits, and the limits shape what we can claim with confidence. Dust blocks optical light in the plane, magnetic fields scramble charged particle paths, and faint backgrounds blur into noise, so interpretation must be cautious and cross-checked. So we combine methods, because the galaxy rarely yields to a single measurement. We compare star motions with gas maps, gamma rays with dust, and local particle measurements with all sky backgrounds, looking for agreements that survive different assumptions and instruments. The goal is not a simple inventory of objects, as if we were counting stars on a clear night. The goal is a physical picture of what surrounds the solar system along the galaxy's vertical axis, including how matter, fields, and radiation exchange energy. That picture has stakes that reach beyond curiosity, because environment shapes risk and opportunity. Radiation from high latitudes can affect planetary atmospheres and spacecraft electronics, and it sets the baseline hazard for exploration as we push farther from Earth's protective magnetosphere. Gravity from the disk and halo shapes our orbit, and it shapes the orbits of everything nearby. It sets the rhythm of mid-plane crossings, and it influences which regions of the galaxy we traverse, subtly steering our long-term neighbourhood through dynamical constraints. Even our sense of cosmic neighbourhood depends on this layered context, because nearby is not only distance. A nearby supernova is not just a point in space, but an event embedded in disk structure and timing, with its effects filtered by magnetic fields and intervening gas. So we return to the opening paradox with sharper terms and with better questions. There is no universal up, yet there is a galactic up that changes what reaches us, and a galactic down that changes what we pass through. Above us lies a sky that can be quieter in dust, but louder in high-energy backgrounds, where distant signals are less muffled by the plane. Below us lies a denser layer that can tug, compress, and disturb, where clouds and star formation concentrate and where gravity steepens. The solar system sits between these regimes, and it does not stay fixed between them. It is a moving platform, sampling different heights and different conditions as the galaxy turns, while the sun's vertical oscillation slowly carries us through changing densities. We will follow that motion and those signals because they are two sides of the same structure. We will ask what fills the halo, what hides in the disk, and what arrives from beyond both, using the vertical axis as our organizing thread. Next, we begin with the plane itself. We trace how the Milky Way's disk is built, and why its thinness makes the vertical direction so revealing, especially when we compare what we see in starlight with what we infer from gravity and high-energy messengers. In Chapter 1, above and below became directions relative to the galactic plane. Now we test that idea close to home, where emptiness should be simplest, and geometry should feel intuitive. Within a few hundred light years, space is already structured, magnetized, and reactive, more like weather than vacuum. The solar system travels through an interstellar environment that changes with time and position, and it responds like a boat crossing shifting currents. Our first boundary is not the galaxy, and it is not even the nearest star. Our first boundary is the sun's wind, a flow that turns the solar system into an active object. The solar wind is a continuous outflow of charged particles and magnetic field, launched from the hot corona above the solar surface. Protons and electrons stream outward at hundreds of kilometers per second, and embedded within them is the interplanetary magnetic field, an extension of the sun's magnetism carried into space. Near Earth and the inner planets, this wind is typically supersonic, meaning it moves faster than pressure waves can travel through it. That single fact changes everything, because supersonic flows do not adjust gently. They form shocks, they generate turbulence, and they convert directed motion into heat when they finally slow down. The wind expands outward, thins with distance, and still carries the sun's influence far beyond Neptune, past the Kuiper belt, and into the dim outskirts where sunlight is only a bright star. This outflow inflates a cavity in the surrounding interstellar medium, and the cavity is not merely empty space. It is filled with solar wind plasma, magnetic fields, and a population of energetic particles accelerated by shocks and turbulence. That cavity is the heliosphere, a moving bubble shaped by pressure balance, and it is sculpted by the wind's collision with the galaxy's local gas. Inside it, the solar wind dominates particle densities and magnetic conditions, and it sets the rules for how charged particles move. Outside it, the galaxy's local gas and field take over, and the sun becomes just one source among many. If we could see it, the heliosphere would not look like a perfect sphere. It would look like a comet-shaped wake, with a blunt nose facing the incoming interstellar flow and a long, complicated tail. The shape depends on the external pressure, the interstellar magnetic field direction, and the sun's own time variable output. Even the word bubble is slightly misleading, because the boundary is layered and porous, and its edges are constantly being rewritten. The solar wind does not remain supersonic forever, because it loses momentum as it expands. Far from the sun, it slows abruptly at the termination shock, a collisionless shock formed not by particle impacts but by electromagnetic forces. The shock marks where the wind's bulk speed drops, and its energy becomes heat and turbulence, and it also becomes a site of particle acceleration. Beyond that region, the solar wind is subsonic and more easily deflected. Like a river that has hit a broad, shallow delta, past the termination shock lies the heliosheath, a thick boundary layer of disturbed plasma. Here the solar wind piles up, mixes and drapes around the obstacle ahead, and the magnetic field lines become compressed and tangled. The obstacle is not a wall of rock, and it is not a solid barrier. It is the pressure of interstellar plasma, neutrals, and magnetic field, pushing back with its own momentum and magnetism. In this region, turbulence can be strong, and the flow can become asymmetric, responding to the interstellar field like fabric stretched over a frame. The outermost boundary is the heliopause, where solar wind pressure yields to interstellar pressure, and where the sun's domain ends. It is not a perfect sphere, and it is not static, because both sides of the boundary vary. The sun's 11-year activity cycle changes the wind's pressure and magnetic polarity, while the surrounding interstellar flow changes as we move through space. The heliopause can ripple, reconnect, and leak particles across, and its exact position can shift by astronomical units over time. This boundary is also an electrical and magnetic interface, not simply a change in density. On one side, the magnetic field is carried outward by the solar wind, wound into a spiral by the sun's rotation. On the other, the interstellar magnetic field arrives with its own orientation and tension, like a taut line pulled across the heliosphere's nose. Where these fields meet, reconnection can occur. Field lines can break and rejoin, allowing energy and particles to cross a boundary that otherwise looks sharp. Voyager 1 and Voyager 2 turned this boundary from theory into measurement, and their journey is a reminder of how slowly the solar system's outskirts reveal themselves. Launched in 1977, they were designed for planetary flybys, yet their most enduring work came decades later in the dark beyond the planets. Their instruments tracked particle populations, plasma waves, and magnetic fields as they approached the edge, measuring the heliosphere as a physical object rather than a diagram. Voyager 1 saw a sharp drop in solar wind particles and a rise in galactic cosmic rays, a signature that the shielding effect had weakened. Voyager 2 crossed later and confirmed the boundary's variability, showing that the heliosphere's edge is not identical in all directions. The Voyagers also revealed a key surprise about the magnetic field, and it forced modelers to rethink the boundary's geometry. The field direction did not rotate as dramatically as some models expected at the crossing, even though the plasma populations changed abruptly. That implied strong magnetic draping and a complex geometry at the boundary, where the interstellar field wraps around the heliosphere rather than cutting cleanly across it. It also implied that inside and outside can share aligned field directions across a thin interface, complicating the idea of a simple magnetic wall. Plasma density outside the heliopause was inferred from plasma wave measurements, a clever method that listens rather than looks. Voyager detected oscillations that indicated a denser interstellar plasma than the heliosheath, because the characteristic frequency depends on electron density. That density helps set the pressure balance that defines heliosphere size, and it constrains how the local interstellar medium is ionized. It also tells us something about the environment's history, because ionization depends on radiation fields, shocks, and the slow recombination of electrons with ions. These measurements matter because the heliosphere is a radiation filter, and it is not equally effective for all particles. It modulates lower energy cosmic rays, especially during periods of high solar activity, when the heliospheric magnetic field is stronger and more disturbed. It deflects many charged particles, but not all of them, and the highest energy cosmic rays pass through almost as if the heliosphere were not there. The heliosphere is a shield with seams, and its seams change with time, which means Earth's radiation environment is partly a product of boundary physics. When cosmic rays are modulated, the effect is subtle but measurable, and it is tied to the Sun's magnetic polarity cycle. Charged particles drift differently depending on the global field configuration, and their paths become longer and more tangled during active periods. That changes the flux reaching the inner solar system, which in turn influences atmospheric chemistry and radiation exposure for spacecraft. The heliosphere becomes, in a real sense, part of the space climate that surrounds our planet. The heliosphere also interacts with neutral atoms that ignore magnetic fields, and that interaction is one of the most elegant diagnostic tools we have. Interstellar neutral hydrogen and helium can stream inward, unaffected by Lorentz forces, because they carry no net charge. Some are ionized near the Sun by ultraviolet radiation or by charge exchange, and they become pickup ions, suddenly forced to gyrate around magnetic field lines. That process injects new particles into the solar wind, adding mass and altering the flow, especially in the outer heliosphere. Others survive long enough to be measured directly by spacecraft, arriving as a faint, steady wind of atoms. Helium is particularly valuable because it is less affected by radiation pressure than hydrogen, and it traces the interstellar flow more cleanly. In the inner solar system, these neutrals can form a gravitational focusing cone downstream of the Sun, a subtle enhancement that reveals both the flow direction and the temperature of the incoming gas. Even here, empty space behaves like a medium with currents, gradients, and wakes. This brings us to the local interstellar cloud, often called the local fluff, a name that hides how important it is. It is a small, warm, partially ionized cloud of gas and dust, with a temperature of several thousand Kelvin, warm by terrestrial standards, cool compared with million-degree plasma. The solar system is embedded within it, moving through it at tens of kilometers per second, and that relative motion defines an incoming interstellar wind. Its density and ionization state shape the heliosphere's size and asymmetry, because external pressure determines how far the solar wind can push outward. The local fluff is not an abstract concept, and it is not inferred from a single technique. It is measured through absorption lines toward nearby stars, where interstellar atoms imprint narrow features on starlight. It is also measured through in situ neutral atom detections, where spacecraft directly count atoms that originated outside the heliosphere. The cloud is a dense knot within a much larger cavity, and its very existence suggests that the local bubble is not uniformly hot. Embedded warm clouds can survive inside hot plasma, possibly protected by magnetic fields and by the physics of conduction at interfaces. Spacecraft have mapped this interaction in multiple ways, and each method reveals a different layer of the same boundary story. Ulysses measured interstellar helium flow through the inner solar system, using a detector that could distinguish neutral helium from other particles. It found a consistent incoming direction and speed, defining a local interstellar wind that is remarkably stable on human timescales. Those parameters anchor models of how the heliosphere is oriented in galactic space, including which side is upwind and which side trails into the heliotail. IBEX extended this by imaging energetic neutral atoms from the boundary region, turning distant interactions into a sky map. These atoms are created when charged particles exchange electrons with neutrals, a process that converts a magnetically trapped ion into a free-flying neutral. Because they are neutral, they travel in straight lines to detectors, preserving directional information like photons do. IBEX turned the heliosphere's edge into a global map rather than a single crossing, and it revealed structure that no one could have inferred from a lone trajectory. IBEX also found the ribbon, a bright arc of energetic neutral atoms across the sky, and its discovery was a genuine surprise. The ribbon likely traces where the interstellar magnetic field is perpendicular to our line of sight, enhancing the production or retention of energetic particles in specific regions. It implies that the local field geometry strongly shapes boundary interactions, and it suggests that the heliosphere is embedded in a larger magnetic environment with coherent structure. In other words, the heliosphere's shape is not only a product of the Sun, but also a response to the galaxy's nearby magnetic scaffolding. Dust grains also penetrate the heliosphere, though not freely, and their behavior is a lesson in scale. A dust grain can be electrically charged by sunlight and plasma interactions, which means magnetic fields can influence it despite its mass. Some grains are filtered by electromagnetic forces and radiation pressure, especially the smallest ones with high charge-to-mass ratios. Others drift inward and are detected by dust instruments on spacecraft, arriving like microscopic messengers from outside. Their trajectories encode both the interstellar flow and the heliosphere's electromagnetic filtering, and they remind us that space weather includes solid matter. So even at the smallest scale of above and below, we find a layered interface that behaves like a boundary ecosystem. Solar wind plasma, interstellar neutrals, dust, and magnetic fields overlap in a moving boundary zone, and none of them fully dominates everywhere. The boundary is not a clean membrane, and it is not a single surface you can draw with confidence. It is a region where charge exchange, turbulence, and reconnection constantly rewrite conditions, and where the same location can behave differently as the solar cycle turns. Now we zoom out to the medium beyond the heliopause, where the Sun's influence fades into the galaxies. The interstellar medium is not one substance, and it is not uniform even over small distances. It is a set of phases, shaped by heating, cooling, shocks, and magnetic pressure, and those phases coexist in pressure balance that is often imperfect. It includes cold molecular clouds where stars form, warm neutral and ionized gas that fills much of the disk, and hot ionized plasma that occupies large volumes despite its low density. Dust is a small fraction by mass, but it dominates many observations and it shapes the galaxy's appearance. It absorbs starlight and re-emits in infrared, which means it both hides and reveals structure depending on wavelength. It also provides surfaces for chemistry, helping molecules form in cold clouds, and it helps cool dense regions by radiating away energy. Its alignment with magnetic fields lets polarization trace field directions, turning starlight into a compass for invisible forces. Magnetic fields thread every phase of the ISM and influence how gas moves, especially when the gas is ionized. They guide charged particles and resist compression, altering how clouds collapse and how shocks propagate. They store energy and transmit disturbances through waves, including alpha waves that carry tension along field lines. They also shape cosmic ray propagation, turning straight paths into diffusive wandering, and that diffusion depends on turbulence that can be driven by supernovae and stellar winds. Within this complex medium, the solar system sits inside a much larger cavity, and that cavity changes the meaning of local. This cavity is the local bubble, an irregular region of hot, tenuous plasma that surrounds us in many directions. Its characteristic temperature is around 1,000,000 Kelvin, hot enough that atoms are highly ionized and collisions produce soft X-ray emission. Its density is far lower than typical warm clouds in the disk, which means it contains little mass despite occupying a large volume. The local bubble is large on human scales and small on galactic scales, and that contrast matters for intuition. It spans on the order of hundreds of light years across, depending on direction, which makes it a dominant feature of our immediate neighbourhood. It is not centred perfectly on the Sun, and its edges are uneven, like a cavity carved into wood with splintered boundaries. It is a carved-out volume within the galactic disk's gas layer, and the disk itself is stratified, denser near the plane and thinner away from it. Evidence for the local bubble first emerged from the soft X-ray background, a discovery that arrived with the early era of space-based astronomy. Early detectors saw diffuse X-ray emission that seemed to fill the sky, even where no obvious sources existed. Hot plasma at about 10 or 6 Kelvin naturally emits soft X-rays through thermal processes, including bremsstrahlung and line emission from highly ionized atoms. A local cavity of hot gas could explain a significant fraction of that glow, because nearby emission would not be heavily absorbed by intervening material. This interpretation became more complicated with time, and the complication was itself a lesson in boundary physics. Some soft X-rays come from solar wind charge exchange within the heliosphere, where highly charged solar wind ions steal electrons from neutral atoms. That local foreground can mimic diffuse emission from interstellar plasma, and it can vary with solar wind conditions. Separating heliospheric and interstellar contributions required careful modelling and multiple datasets, including time variability and comparisons across different lines of sight. Even with those complications, the local bubble remains supported by independent mapping, and the convergence of methods is persuasive. Three-dimensional dust reconstructions show a surrounding shell of higher dust density, like a faint ring around a dim interior. Nearby stars provide reddening measurements that can be inverted into spatial dust distributions, because dust slightly dims and reddens starlight in a distance-dependent way. The maps reveal a cavity around the Sun with denser walls beyond, and the cavity's irregularity becomes visible as you rotate the view. Radio and ultraviolet observations add more constraints, and they fill in the missing pieces of the puzzle. Absorption lines toward nearby stars show low column densities in many directions, which indicates a relative lack of cool, dense gas near the Sun. In ultraviolet spectra, species like neutral hydrogen, ionized magnesium, and other traces reveal both temperature and ionization state. The warm local fluff sits within a larger region that is unusually evacuated, and that evacuation is hard to explain without energetic events. The local bubble is not simply empty, and it is not simply hot, because real astrophysical cavities are messy. It is filled with hot plasma, magnetic fields, and embedded warm clouds, and those clouds can be shredded or shaped by their surroundings. It is also threaded by flows and interfaces where hot and warm phases meet, and those interfaces can be thin but powerful. They can produce emission lines and enhance certain interactions, and they are places where the ISM's complexity concentrates. If the bubble is a room, its walls and corners are where the action happens. How does such a cavity form in a disk that normally contains abundant gas and dust, and why does it persist? The leading explanation is supernova excavation, a process that is violent, cumulative, and surprisingly efficient. Multiple explosions over millions of years can sweep up surrounding gas, creating an expanding superbubble. Their shocks heat and rarefy the interior while piling material into a shell, and the shell can become a long-lived structure. The interior remains hot because low density slows radiative cooling, allowing million-degree plasma to persist. This is supernova archaeology, reconstructed from stellar motions and local structures, and it relies on the fact that stars move in groups. Nearby stellar associations, especially the Scorpius-Centaurus complex, are plausible sources because they contain massive stars with short lifetimes. Massive stars form in groups and die in sequences, and their winds can precondition the medium even before the first explosion. A chain of supernovae can create a superbubble that expands and overlaps older cavities, and the resulting structure can become a network rather than a single sphere. Models suggest the local bubble was carved by several supernovae, not one, and the number matters for timing and temperature. Each explosion adds energy, reheats cooling gas, and pushes the boundary outward, while also stirring turbulence that mixes material. The combined effect can maintain million-degree plasma for extended periods, even as the bubble expands and its interior density drops. It can also create openings where hot gas vents into larger cavities, especially if the surrounding medium is already structured. We have a tangible clue that at least one nearby supernova occurred, and it arrived not from a telescope but from geology. Iron-60 isotopes have been found in deep-sea sediments and other terrestrial archives, preserved in layers that can be dated. Iron-60 is radioactive and decays on million-year timescales, so it cannot be primordial in Earth's crust. Its presence suggests deposition of fresh supernova material within the last few million years, delivered through interstellar dust grains that survived the journey. This is not a perfect smoking gun for a single event, and the uncertainties are part of the story. Transport through interstellar space, dust grain survival, filtering by the heliosphere, and deposition on Earth all add complexity to the chain of evidence. Yet the signal is difficult to explain without nearby stellar explosions, and it aligns with the idea of recent activity in our neighbourhood. It turns the local bubble from a distant inference into a local history written in atoms, and it invites a quiet question about how often Earth has been dusted by stellar ash. The local bubble's walls are as important as its interior, because boundaries are where energy becomes structure. As shocks expand, they sweep up gas and dust into denser shells, and those shells can cool and fragment over time. They can also compress pre-existing clouds, potentially triggering star formation in nearby regions, although the details depend on timing and geometry. In visual terms, the bubble is not just a cavity, but a cavity with a rim, a faint, uneven ring of accumulated material. Several nearby molecular clouds sit near the bubble's boundary, and their placement is suggestive rather than random. Their distances and shapes often align with the cavity's inferred edges, as if they were pushed, sculpted, or confined by expanding flows. This suggests a relationship between the bubble's expansion and local cloud structure, even if the causal chain is complex. The walls are not smooth, and they intersect with other bubbles and flows, producing knots and filaments that can persist for millions of years. These boundary regions also matter for high-energy particles, because cosmic rays respond to both gas density and magnetic structure. Cosmic rays propagate through the ISM by scattering on magnetic turbulence, and that scattering sets how quickly they diffuse. Changes in density and magnetic structure alter their diffusion, and a shell with enhanced field strength can act like a partial barrier. The result can be a local modification of cosmic ray spectra, subtle in measurement but significant in interpretation. When cosmic rays collide with gas, they produce gamma rays and secondary particles, and the brightness depends on how much target material exists. Denser walls provide more targets for these interactions, which can create enhanced emission compared to the bubble's interior. It also means the bubble's geometry can influence the radiation environment near the solar system, not by generating cosmic rays, but by shaping how they travel. In this way, a structure hundreds of light-years wide can still matter to a planet. Soft X-ray emission can also be stronger near interfaces, and the reason is rooted in basic thermodynamics. Hot plasma touching cooler material creates mixing layers and conductive boundaries, and both processes can populate intermediate temperatures that radiate efficiently. Those regions can radiate in soft X-ray and extreme ultraviolet bands, producing a glow that traces contact zones rather than bulk interiors. The bubble's walls become luminous not because they are bright objects, but because they are active boundaries. The brightest lines often come from the places where phases are colliding and negotiating terms. The local bubble is not symmetric above and below the galactic plane, and its asymmetry is a clue to the disk's layered nature. Its shape reflects the disk's stratification and the locations of its driving explosions, which likely occurred in specific associations and trajectories. In some directions, it appears to open into larger low-density regions, where the cavity becomes less confined. These openings are often described as chimneys that connect the disk to the halo, and the metaphor is apt because they channel flow. Chimneys are pathways for hot gas to vent vertically, and they are a natural outcome of repeated supernova activity. Supernovae in the disk can punch through the denser midplane layers, especially if earlier explosions have already weakened the region. Hot plasma then rises into lower density regions above and below the plane, buoyed by pressure gradients and guided by magnetic fields. This is one way the galaxy circulates energy and matter between disk and halo, and it helps explain why the halo is not a static reservoir. This vertical connection is our first concrete hint that above is a different regime, not merely a direction. Above the plane, densities drop and cooling changes, so hot gas can persist longer and expand more freely. Magnetic field geometry can become more ordered on large scales, even as turbulence persists locally. High-energy particles can travel differently, and backgrounds can become cleaner of dust absorption, revealing emissions that are hidden when we look through the crowded midplane. The local bubble may connect to neighbouring cavities that extend farther from the plane, and the connections matter as much as the cavities themselves. The local chimney concept links our cavity to a network of superbubbles, some created by other associations and earlier epochs. These structures overlap, merge, and evolve as new supernovae occur, producing a porous, foam-like disk. The solar system's local environment is part of a larger porous disk, and porosity is a property of repeated violence. Porous does not mean safe, and the word bubble should not lull us into thinking of protection without conditions. A cavity can reduce encounters with dense clouds, but it can also expose us to different radiation fields and different cosmic ray transport conditions. The heliosphere's size depends on external pressure, which changes between clouds and cavities, and that size affects how well it modulates lower energy cosmic rays. A denser cloud could compress the heliosphere and weaken its modulation, while a more rarefied region could let the heliosphere expand. This makes the protective cocoon time-dependent, and the time dependence operates on multiple clocks. The sun's activity changes the solar wind and the heliosphere's strength, and it does so on decadal cycles that we can measure directly. The interstellar environment changes as the solar system moves through different clouds and phases, and that happens over thousands to millions of years. Over long times, even small density differences can alter what reaches the inner planets, and the cumulative effect becomes part of Earth's long environmental story. We can frame this as a sequence of nested bubbles, each one carved by a different engine. The heliosphere is carved by the sun into the local fluff, and its boundaries are defined by shocks and magnetic interfaces. The local fluff is embedded in the local bubble's hot plasma, a warm island inside a hotter sea. The local bubble is carved into the galactic disk by supernovae, and its walls are built from swept-up matter. Each layer has its own boundaries, and each boundary is leaky, because nature rarely builds perfect seals. The central question returns with sharper edges because above and below now has a tangible meaning. What exists above and below is not just distant halo gas or dark matter, and it is not only a faraway diagram in a textbook. It is also the near-field architecture that filters particles and radiation before they ever reach Earth, and that architecture begins at the heliopause. The first answers are local, and they are already complex, which should make us cautious about simple pictures at larger scales. Historically, this shift from emptiness to structure took decades, and it unfolded step by step as instruments improved. Early space probes hinted at a solar wind and an interplanetary magnetic field, confirming ideas that had once been controversial. Later missions measured pickup ions, energetic neutrals, and boundary crossings, turning theoretical interfaces into measured environments. Meanwhile, X-ray astronomy and dust mapping revealed cavities and shells in the nearby ISM, showing that our neighbourhood is shaped by past explosions. The story is not only discovery, and it is not only accumulation of data, it is also correction, because each new measurement exposed assumptions that were too simple. Soft X-ray maps had to account for heliospheric foregrounds, and that forced astronomers to separate local and interstellar emissions carefully. Bubble models had to incorporate irregular geometry and embedded clouds, acknowledging that the ISM is clumpy even inside cavities. The more we measured, the less the local environment resembled a simple spherical cavity, and the more it resembled a living boundary zone. The local bubble also reframes our sense of neighbourhood, because it ties nearby stars to the medium between them. Nearby stars are not just points at known distances, and they are not isolated actors. They are members of moving groups that once formed together, sharing trajectories that can be traced backward in time. Their deaths can sculpt the medium we now inhabit, leaving cavities, shells, and isotope traces that persist for millions of years. In that sense, the night sky contains both the survivors and the evidence of those that are gone. This is why above and below cannot be treated as empty directions, even before we leave the solar neighbourhood. Even locally, the galaxy is layered and scarred by explosions, and those scars channel flows and shape magnetic fields. The solar system rides inside a carved-out volume, shielded by a wind-blown bubble that is never fully sealed. Our motion through this medium is slow, but the consequences accumulate, and the boundary conditions of space become part of our long-term environment. So the paradox resolves into a better question. If our local space is shaped by supernovae and magnetic boundaries, what happens as we climb farther from the disk? What does the Milky Way look like in the vertical direction when we map gas, fields, and high-energy emission together? Next, we follow the chimneys and cavities upward and downward from the plane. We move from the local bubble to the galaxy's thicker layers, where hot halos, cosmic rays, and magnetized outflows become the dominant architecture. We leave the local bubble and keep climbing, because the disk is not a single sheet. The Milky Way is stacked in layers, each with its own density, chemistry, and radiation rules. Above and below now mean moving through those layers, not drifting into emptiness. In a wide-field view, the galaxy stops looking like a flat painting and starts resembling a stratified atmosphere. The change is subtle at first, just fewer stars per square degree, but it accelerates with height. Gravity, pressure, turbulence, and magnetic fields negotiate a compromise, and that compromise becomes the vertical structure we fly through. The first layer is the thin disk, the galaxy's working surface where most action happens. It holds most cold gas, most dust, and most ongoing star formation in the Milky Way. Its vertical scale height is small, roughly 100 to 300 parsecs for young stars and cold gas. That is only a few hundred to about 1,000 light-years, thin compared with the disk's width. If the Milky Way were a city, this would be the crowded downtown, bright, noisy, and constantly under construction. The thin disk is also where the interstellar medium is most structured, because compression and cooling can actually win. The thin disk is where molecular clouds live, because molecules need shielding and density. Hydrogen can pair into H2 only when dust and self-shielding block destructive ultraviolet photons. Dust grains are not just soot in space, they are chemical workbenches where atoms meet and bond. Dust also absorbs ultraviolet light and helps gas cool so clouds can collapse into stars. Cooling matters because gravity needs an exit for energy. Otherwise, pressure pushes back and collapse stalls. In the densest pockets, temperatures fall to tens of Kelvin, and sound speeds drop enough for fragmentation to begin. The densest clouds collect along spiral arms, where gas is compressed and star formation is triggered. Spiral arms are patterns in the rotating disk, but they still organize where the gas piles up. As gas orbits the galactic center, it drifts into these density waves and gets squeezed, like traffic bunching at a bottleneck. That squeezing raises density, strengthens shielding, and shortens the time it takes gravity to gather material. In visible light imagery, the arms announce themselves with blue star clusters and glowing H2 regions. In radio and infrared maps, the same arms appear as lanes of cold molecular gas threaded with dust. This is why the Milky Way band in the night sky hugs a line across the heavens. We're embedded inside the thin disk, so looking along the plane means looking through the most stars. The line is not a boundary on the sky, but the long axis of our own neighbourhood stretched by perspective. Dust dims and reddens that starlight, but the sheer number of stars still produces a bright band. In dark sights, you can see it split and knot, bright star clouds interrupted by ink-black rifts. Those rifts are not holes in the galaxy, they are nearby dust lanes blocking the distant glow. Looking away from the plane exits the dense layer quickly, and the sky becomes clearer but fainter. The star count drops because the path length through the thin disk collapses from tens of thousands of light-years to a few hundred. The colour of the sky changes too, because extinction falls and bluer light survives. At high latitude, the Milky Way's light becomes less a river and more a scattered spray. The same geometry that makes the galactic plane bright also makes it confusing, because many structures overlap along the line of sight. Above and below, the view simplifies, and the galaxy begins to read like a layered diagram. The thin disk is not only stars and clouds, but also a set of gas phases stacked by pressure. Cold molecular gas sits closest to the midplane because it is dense and heavy. Warm neutral and warm ionized gas extend higher, supported by turbulence and magnetic pressure. Above that, hot ionized gas fills cavities carved by stellar winds and supernovae. These phases are not neatly separated like geological strata, yet the trend is real and measurable. As you climb, the gas becomes hotter, thinner, and more ionized, and the dominant forces shift with it. In the cold phase, densities can reach hundreds or thousands of particles per cubic centimeter. In the warm phases, densities fall by orders of magnitude, and the gas becomes more responsive to fields and waves. In the hot phase, the plasma can be so tenuous that particles travel long distances before colliding. That low collision rate changes how energy moves, because conduction and mixing become as important as radiation. Visually, the cold gas hides in dark lanes, while the warm ionized gas glows in faint emission lines. The hot plasma, by contrast, is mostly invisible unless you look in X-rays or trace it by its effects. The midplane is where gravity is steepest over short vertical distances. That steepness is why the Sun oscillates above and below the plane over tens of millions of years. The motion is not a plunge but a slow bobbing, like a buoy rising and falling on a long swell. Each oscillation changes the density and radiation environment around the heliosphere, even if the change is gradual. The difference is not dramatic on human timescales, yet it matters for what gas and dust the solar system encounters. In the thin disk, down toward the midplane means more targets for cosmic rays and more places for massive stars. The thin disk's crowdedness also shapes what we can measure. In the plane, extinction hides distant stars so optical surveys can miss whole populations. Radio, infrared, and gamma-ray maps become essential because they cut through dust or bypass it entirely. Historically, this is why our understanding of the galaxy arrived in layers. First optical star counts, then radio hydrogen, then infrared dust. Every new wavelength peeled back another veil, and each veil turned out to be a physical component. The disk is not only where stars form, it is where our view is most strongly filtered. But the thin disk is only the first layer in the stack. As we climb farther, the population of stars changes, and the galaxy's history starts to show. The next layer is the thick disk, a component that is physically thicker and chemically different. It is not a separate galaxy glued on top, but a distinct phase of the Milky Way's own assembly. You can think of it as a memory of earlier conditions, preserved in stellar orbits and elemental ratios. The transition is gradual in space, yet sharp in meaning. The thick disk has a scale height of roughly 1 kiloparsec, around 3,000 light-years. Its stars are older on average, and they tend to have higher random motions. They orbit the galaxy with more vertical energy, so they spend more time above and below the plane. The thick disk is not just the thin disk stretched out, but a distinct population. In kinematic terms, its stars are hotter, meaning their velocities are more dispersed and less orderly. In a time-lapse of galactic history, this layer looks like the disk before it fully settled. Chemistry is the fingerprint that tells us the thick disk formed differently. Thick disk stars are often more alpha-enhanced at a given ion abundance, reflecting faster early enrichment. Alpha elements like oxygen, magnesium, and silicon are made efficiently in core collapse supernovae from massive stars. Iron, by contrast, builds up more slowly when type higher supernovae begin contributing on longer timescales, so an alpha-enhanced pattern implies rapid star formation, fast enough that massive stars dominated enrichment early on. It also implies that the galaxy's early disk was stirred and heated. That chemical story became clearer as stellar spectroscopy improved. Large surveys turned the sky into a laboratory, measuring elemental abundances for millions of stars. With those data, the thick disk stopped being a vague geometric idea and became a population with a timeline. The stars themselves became clocks, because their compositions encode the pace of earlier supernova activity. When you see alpha enhancement, you are seeing the imprint of short-lived massive stars on a still-forming disk. The thick disk is, in that sense, a fossil atmosphere. Heating can happen through internal processes, but the thick disk hints at external disturbance. Minor mergers can thicken a disk by gravitational shaking, raising stellar orbits. A passing dwarf galaxy does not need to collide head-on. Tides and resonances can do the work. Gas-rich accretion can also build a thicker component during early turbulent phases. In the early universe, galaxies were fed by clumpy inflows, and disks were more chaotic than the one we see today. The thick disk becomes a fossil record of a rougher Milky Way when the disk was less calm and more chaotic. The thick disk also changes what above means for radiation and particles. Fewer molecular clouds means fewer dense targets, but more volume filled by warm and hot gas. Dust extinction drops, so ultraviolet and optical lines of sight become cleaner, yet the environment becomes more ionized, and magnetic turbulence can change how charged particles scatter. In practical terms, photons travel farther before being absorbed, and charged particles meet fewer collisions with neutral gas. The thick disk is a transitional zone, still connected to the plane, but already leaning toward halo conditions. Above the thick disk, the stellar halo takes over, and the galaxy looks almost empty in starlight. The halo is sparse, extended, and dominated by old metal-poor stars. Its stars do not trace the disk's rotation cleanly, because their orbits are more random and often elongated. Instead of circling in a thin band, many halo stars dive in and out on tilted paths. The halo is not where the Milky Way makes most of its new stars today. It is where the galaxy keeps its oldest witnesses, moving in quiet, long arcs. The halo is also where the Milky Way's cannibal history is easiest to read. Streams of stars arc across the sky, remnants of dwarf galaxies torn apart by tides. These streams preserve coherent motions for a long time, because the halo is low density. The stars in a stream are separated in space, yet they remain linked by a shared orbit, like beads stretched along a wire. With modern astrometry, we can see these structures not just as overdensities, but as moving patterns. Each stream is a record of accretion, telling us the galaxy grew by consuming smaller systems. There is a historical irony here. For much of the 20th century, the Milky Way was imagined as a mostly isolated system, with a simple disk and bulge. Then deeper surveys revealed faint substructures, and the halo turned into a map of past collisions. The idea of hierarchical assembly, galaxies built by mergers, stopped being abstract and became visible overhead. When you look at a halo stream, you're watching gravity finish a meal that began billions of years ago. The sky becomes an archaeological site, and the artifacts are still moving. Globular clusters live in this regime as well, dense star swarms that are among the oldest objects we can date. Many orbit far above and below the plane, and some may have been accreted with their parent dwarfs. Their ages and compositions constrain early star formation and early chemical enrichment. Because globular clusters are compact and bright, they were among the first halo objects catalogued. Yet even they carry surprises, including multiple stellar populations that hint at complex formation histories. In the halo, the Milky Way's past is written in orbital debris, yet the halo is not only stars, and the most important mass there is not luminous. The dark matter halo envelops the disk and extends far beyond the visible galaxy. It dominates the gravitational potential at large radii and helps explain the Milky Way's rotation curve. That rotation curve, flat rather than falling, was one of the clues that forced astronomers to accept unseen mass. It also shapes vertical motion by contributing to the restoring force that pulls objects toward the plane. Even when starlight thins out, the gravitational landscape remains deep and structured. Dark matter does not make a bright layer, but it creates a deep gravitational basin. That basin holds the disk together and sets the scale for the halo's extent. It also influences how the outer disk warps and flares, because the disk responds to the halo's shape. If the halo is slightly flattened or lopsided, the disk can bend in response over tens of thousands of light years. Above and below, gravity is still present, even when the view looks empty. The galaxy's visible layers are like foam on a much larger, darker sea. There is another halo too, made of gas rather than stars. Galaxies are surrounded by extended gaseous envelopes, because gas is hard to keep confined to the thin disk. Stellar feedback pushes it outward, accretion brings it inward, and gravity tries to hold it all together. This is the circumgalactic medium, the CGM, and it is a major reservoir of baryons. It is also a boundary layer, where the Milky Way negotiates with intergalactic space. If the disk is a workshop, the CGM is the warehouse and loading dock. The hot gas halo is often at million-degree temperatures, a plasma too hot for molecules and too thin for bright emission. At those temperatures, atoms are stripped of many electrons, and the gas radiates mainly in X-rays and ultraviolet lines. We detect it through soft X-rays and through ultraviolet absorption lines against background sources. Highly ionized oxygen and other ions trace this phase, because their transitions are sensitive to hot, diffuse gas. In practice, the halo becomes visible as a set of shadows and faint glows rather than a bright object. You do not see it as a cloud, you infer it as a fingerprint stamped on someone else's light. The CGM matters because it is part of the galaxy's supply chain. It stores gas that can cool and fall back to the disk, feeding future star formation. It also receives gas and metals expelled from the disk by supernovae and winds. Without a CGM, galaxies would either run out of fuel too quickly or fail to explain where their missing baryons reside. This missing baryon problem is not about dark matter. It is about ordinary matter that is simply hard to see. A hot, diffuse halo can hide enormous mass in plain sight because it barely glows, so the galaxy is layered in stars and layered in gas, and the layers are connected by flow. The connection is not smooth, because the disk is punctured by violence. Clustered supernovae and a massive star winds carve superbubbles in the thin disk's gas. When enough energy is injected in one region, a cavity grows faster than it can cool. The result is a pressure-driven expansion that turns a star-forming region into a temporary engine of excavation. The disk, which looks continuous from afar, is actually riddled with these evolving voids. A superbubble expands into the surrounding medium, sweeping up a shell and heating its interior. The shell can become dense enough to trigger new star formation along its rim, feedback that both destroys and creates. Inside, temperatures rise to millions of degrees, and the gas becomes a tenuous, overpressured plasma. If it grows large enough, it can break out of the disk's denser layers. Breakout happens more easily above and below the plane, because density drops with height. The result is a chimney, a channel that vents hot gas and particles into the halo. Chimneys are not rare exceptions because massive stars form in clusters. A single supernova is dramatic, but a sequence of them is transformative. Each explosion reheats the interior, maintains pressure, and keeps the cavity from collapsing. Over millions of years, superbubbles can merge, creating a porous disk with multiple vertical outlets. From a distance, the disk becomes less a sealed layer and more a leaky membrane. The leaks matter because they set the exchange rate between the star-forming plane and the halo above it. This is where the galactic fountain model enters, and it reframes up as circulation. Hot gas rises buoyantly into the lower density halo, carrying energy and metals. The buoyancy is not magic, it is simply density contrast in a gravitational field, the same principle as hot air rising. As it expands, it cools radiatively and through mixing with ambient halo gas. Cooler fragments and clouds can then fall back toward the disk, returning mass but not necessarily returning it to the same place. The fountain is a conveyor belt with side exits, and it can redistribute material across the galaxy. The fountain is not a perfect loop, and it is not purely vertical. Rotation, turbulence, and magnetic tension can deflect flows sideways. Some gas may cool into high-velocity clouds that rain down at oblique angles. Those clouds are seen in radio surveys as fast-moving hydrogen features, sometimes with uncertain distances and origins. Some may remain hot and join the CGM for long periods, becoming part of a slower reservoir. The boundary between fountain and CGM is not a wall, it is a gradient in time and temperature. This circulation changes the chemical evolution of the galaxy. Metals forged in supernovae are lifted out of the thin disk and dispersed. When gas returns, it can seed new molecular clouds with enriched material. The fountain also mixes accreted low metallicity gas with enriched outflows, moderating the disk's composition over time. Without mixing, the disk could develop sharper chemical contrasts, and star formation would proceed in a more patchy, less regulated way. Instead, the galaxy behaves like a system that stirs its own ingredients, imperfectly but persistently. The fountain also changes the radiation environment above and below the plane. In the thin disk, dust absorbs ultraviolet light and reprocesses it into infrared. Above the plane, dust columns drop, so ultraviolet radiation fields can extend farther. Ionizing photons can leak through low-density channels, changing ionization states in the thick disk and lower halo. This leakage is not uniform because the disk is clumpy, and the chimneys open in specific places, so the halo's ionization can be patchy, shaped by where the disk happens to be porous at a given time. Particle populations change too because the sources and the propagation conditions change with height. Near the plane, cosmic rays are injected by supernova remnants and stellar winds in star-forming regions. Shockwaves accelerate particles by repeated crossings, building power law energy spectra. Above the plane, the density of sources drops, but the volume available for propagation increases. The halo becomes a reservoir where particles can linger. That lingering matters, because it turns the halo into a storage region that smooths out bursts and clusters of activity. To understand that reservoir, we need the galaxy's magnetic architecture, because charged particles follow fields. The Milky Way has an ordered large-scale magnetic field that roughly follows the spiral pattern in the disk. It also has turbulent fields driven by supernovae, shear, and instabilities. The combination creates a tangled maze that turns straight particle paths into diffusion. In plain terms, cosmic rays do not travel like bullets, they wander like smoke in a windy room. The details of that wandering depend on how ordered the field is, and how strong the turbulence becomes. Magnetic fields also have vertical components, and those components matter for above and below. Field lines can arch out of the disk, drape around superbubbles, and connect to the halo. In some regions, chimneys may align with field geometry, making escape easier for hot gas and cosmic rays. In other regions, magnetic tension can confine plasma and slow vertical transport. The field is both a guide and a net, sometimes opening pathways, sometimes tightening them. The difference can determine whether energy stays near the plane or is vented upward. We do not measure galactic magnetic fields by touching them, but by how they act on light. Faraday rotation is one key tool, because magnetized plasma rotates the polarization angle of radio waves. The amount of rotation depends on electron density and the line-of-sight magnetic field component. By mapping rotation measures across the sky, we infer large-scale field patterns and reversals. Those reversals are especially revealing, because they hint at how the field is generated and maintained by galactic dynamos. Even without seeing the field directly, we can reconstruct its geometry from the way it twists passing radio signals. Synchrotron emission is another key tool because relativistic electrons spiral around magnetic fields and radiate. The radio glow of the Milky Way is partly synchrotron, and its spectrum reveals electron energies and field strengths. Polarized synchrotron traces ordered fields, while depolarization and fluctuations reveal turbulence. In full-sky radio maps, the galaxy looks like a luminous web, with filaments and loops rising away from the plane. Some of those arcs likely trace old superbubbles, their edges highlighted by compressed magnetic fields. The sky itself becomes a screen where invisible forces draw visible patterns. Magnetic fields do more than guide particles, because they also support gas against gravity. Magnetic pressure and tension can help hold up warm ionized layers above the plane. They can channel shocks and shape superbubble expansion, affecting whether a cavity breaks out. In the vertical direction, magnetism is part of the scaffolding that sets scale heights. Thermal pressure alone often cannot explain how extended some ionized layers are, especially when cooling is efficient. Add magnetic support and cosmic ray pressure, and the atmosphere of the galaxy becomes easier to hold up. Cosmic rays are the most sensitive tracers of that scaffolding, because their motion is dominated by electromagnetic forces. They diffuse along magnetic field lines and scatter off turbulence, which makes their arrival directions misleading. Their confinement time in the galaxy depends on how effectively the halo traps them. A larger or more turbulent halo can keep cosmic rays longer, changing the spectrum that reaches the solar system. This is why measurements of secondary cosmic ray species are so valuable, because they encode how long particles wandered. The halo, in effect, is part of the galaxy's particle accelerator system, not just the space above it. This is why above can matter for what reaches Earth, even when sources are in the disk. A cosmic ray produced near the plane can spend a long time wandering through the halo before returning. During that time, it can lose energy, fragment, or generate secondary particles through interactions. The halo becomes part of the processing pipeline, not just empty space above the disk. Even the isotropy of cosmic rays at Earth is a clue, because it implies strong scattering and long residence times. The messages we receive have been edited by the medium they travelled through. The same logic applies to gamma rays, which are produced when cosmic rays collide with gas or radiation fields. In the plane, gamma ray emission is bright because gas density is high. Above the plane, emission is fainter but can be cleaner to interpret, because lines of sight are less crowded. Diffuse high-latitude gamma rays become a probe of halo cosmic rays and halo gas. They also help separate local structures from truly extended emission, because distance confusion is reduced at high latitude. In gamma rays, the halo is not just a background, it is a measurable component. The Milky Way also shows large-scale high-energy structures that rise above and below the plane. These structures imply past episodes of strong energy injection, possibly from starbursts or activity near the galactic center. They remind us that the vertical direction can carry signatures of rare events, not only steady fountains. A quiet-looking galaxy can still bear scars, and those scars can persist in hot plasma and non-thermal radiation. When you see a giant lobe or bubble in high-energy maps, you're seeing a time capsule of an energetic episode. The vertical axis is where the galaxy's outbursts can leave their clearest silhouettes. As we climb, the tension in our central question sharpens into a practical difference. Above the plane, the radiation field shifts toward harder backgrounds and longer mean-free paths. Particle populations become more influenced by confinement and escape than by local sources. The magnetic field becomes a guiding rail, steering charged messengers through a three-dimensional maze. In the plane, everything is crowded, so interactions are frequent and signals are quickly altered. Up here, the same signals can travel farther before being absorbed, scattered, or reprocessed. Below the plane is not a different universe, but it is a different column of matter. The disk is roughly symmetric in broad strokes, yet local structures can break that symmetry. Superbubbles can open more easily in one direction than the other, depending on density gradients and nearby cavities. The solar system's offset from the midplane means above and below are not identical even locally. A small displacement changes which clouds, shells, and chimneys lie along our lines of sight. So even in a symmetric galaxy, our particular vantage point can bias what we call up and down. So the paradox resolves into a better question. If the Milky Way is layered, which layer dominates the messages that reach us from high latitude? Which processes lift matter and energy out of the star-forming plane, and which processes return them? Which parts of the vertical stack are highways, and which are traps? And when we detect a high-energy messenger, how much of its story belongs to the source, and how much belongs to the path? In a layered galaxy, travel history can be as important as origin. The thin disk gives us the bright band and the dense targets, but it also hides its own engines behind dust. The thick disk gives us older stars and chemical clues, and it tells us the galaxy was once more turbulent. The halo gives us streams and globulars, and it records accretion that built the Milky Way over time. The hot halo and CGM give us a vast plasma envelope, a baryon reservoir that connects the galaxy to intergalactic space. Each layer is a different experiment in physics, run under different densities, temperatures, and radiation fields. Together, they make a vertical ecosystem, with exchanges that never fully stop. Chimneys and superbubbles connect these layers, turning explosions into circulation. The galactic fountain cycles gas upward and back down, moving metals and reshaping where future stars can form. Magnetic fields thread every layer, and they decide how easily plasma and cosmic rays can cross boundaries. Cosmic rays fill the halo as a reservoir, and that reservoir influences what reaches the solar system from above and below. In this view, the Milky Way is not a static disk with decorations. It is a breathing system with vents and returns. The vertical direction is where the breathing is easiest to see. Now the vertical axis stops being a map feature and becomes a route for the most energetic messengers. If the disk is a crowded city, the halo can be an overpass where signals travel farther with fewer collisions. Gamma rays and neutrinos can arrive from beyond the disk, and the highest energy cosmic rays may prefer paths that avoid the densest gas. The contrast is striking. The plane is bright but noisy, while high latitude is dim but clean. So we climb not to escape the galaxy, but to understand how the galaxy filters what it lets through. What looks like empty space may be the best place to read the message. Next, we treat the halo not as emptiness, but as a detector volume. We follow gamma rays, neutrinos, and ultra-high energy cosmic rays as they enter from high latitude, and we ask what they had to cross. We ask how the layered structure shaped them by absorption, scattering, confinement, and escape. And we ask a final, unsettling question. When a messenger arrives from above, is it truly external, or is it the Milky Way speaking through its own halo? The next step is to listen carefully, because the halo is quiet, but it is not silent. Above the solar system, the sky is not quiet. It is violent in energies we cannot see, measure, or feel directly. In visible light, space can look calm, almost empty, but the high-energy universe is restless. Gamma rays are the sharpest example because they ignore dust and cut through matter that would stop ordinary light. The phrase sounds sensational, yet the physics is precise, testable, and relentlessly consistent. We are surrounded by high-energy light, and our survival depends on a thin layer of air that turns lethal photons into harmless heat. Gamma rays are photons at the extreme end of the electromagnetic spectrum, where wavelength becomes smaller than atoms and energy becomes the defining feature. Their energies start above about 100 keV and extend through MeV, JeV and into TeV. A gamma ray is not a separate substance, only light with very short wavelength and very high frequency. The difference is what that energy does when it meets atoms, molecules, and the fragile chemistry of living tissue. To picture the spectrum, imagine a ruler that stretches from radio waves longer than planets to gamma waves smaller than nuclei. Each step upward in frequency packs more energy into each photon. That energy is quantized, meaning it arrives in discrete packets, not as a smooth drizzle. In plain language, a gamma ray is a single hit that can do real work inside matter. It can arrive alone, but it never arrives gently. At these energies, photons penetrate because they interact less like waves and more like projectiles, although the underlying physics remains quantum. In many materials, lower energy photons are absorbed quickly by electrons in outer shells. Gamma rays, by contrast, can pass through many centimeters of dense matter before being absorbed or scattered. Their probability of interaction depends on energy, atomic number, and thickness, so shielding is a calculation, not a guess. When they do interact, they deposit energy in concentrated, ionizing bursts that leave tracks of disruption. Several interaction channels dominate at different energies, and that detail matters for both biology and detection. At lower gamma energies, the photoelectric effect can dominate, where a photon ejects an electron from an atom. At intermediate energies, Compton scattering becomes common, where the photon ricochets and shares energy with an electron. At higher energies, pair production takes over, where the photon becomes matter and antimatter. In every case, the key outcome is the same. Fast charged particles are created and charged particles tear through chemistry. Biology is vulnerable because cells rely on stable molecular structures and controlled chemistry, especially in DNA and in the membranes that separate inside from outside. Ionization creates radicals, highly reactive fragments, that attack proteins, lipids, and genetic material. Acute exposure can kill tissue by overwhelming repair mechanisms, while chronic exposure raises mutation rates over time. The danger is not that gamma rays are mystical, but that they are efficient at disrupting matter at the molecular scale. Even when DNA is not struck directly, the surrounding water can be split into reactive species that do the damage indirectly. In a visual sense, the harm is invisible, which makes it easy to underestimate. A gamma ray does not burn like a flame, and it does not push like a wind. It passes through skin and bone, leaving only a sparse trail of ion pairs and broken bonds. Yet those microscopic changes can cascade into macroscopic illness. Because biology is an interlocked system, the body can repair a lot, but it cannot repair everything at once. Yet Earth is not exposed to the raw gamma ray sky at the surface, and that fact is one of the quiet miracles of our planet. The atmosphere blocks most gamma rays by forcing interactions high above us, long before they can reach living cells. In the upper air, gamma rays create cascades of secondary particles and lower energy photons. The energy is spread out, diluted through many collisions, and mostly absorbed before it reaches the ground. What arrives at sea level is usually a faint residue, mixed into the background of natural radiation. The shielding works because the atmosphere is thick in mass, even though it feels thin. Above every square meter of ground sits a column of air weighing about 10 tons. To a gamma ray, that column is a long obstacle course of electrons and nuclei. Each interaction steals energy and changes direction, turning a straight-line messenger into a scattered shower. By the time the cascade reaches lower altitudes, it is no longer a single deadly photon, but a fading spray of particles. This shielding is why gamma-ray astronomy had to wait for the space age, and why the history of the field tracks the history of rockets. Optical telescopes can sit on mountains, but gamma-ray detectors must rise above the absorbing air. Early experiments flew on balloons and sounding rockets, catching brief glimpses above most of the atmosphere. Later, satellites could stare for years, building maps photon by photon. This same shield that protects life also hides the most energetic sky, so we learn to observe indirectly. So the paradox resolves into a better question. If gamma rays cannot reach the ground, how do we map them at all? The answer is indirect detection, where we reconstruct a photon story from the debris it leaves. In gamma-ray astronomy, you rarely see the photon itself. You see what it becomes when it finally interacts. At lower gamma-ray energies, detectors work by converting photons into charged particles, because charged particles can be tracked and measured. Above a threshold near 1.022 MeV, a gamma-ray can create an electron and a positron pair. That number is not arbitrary. It is twice the rest mass energy of an electron. Pair production usually occurs near a nucleus that can take up momentum, because conservation laws must be satisfied. Once charged particles exist, we can track them and infer the original photon's direction and energy. The Fermi Large Area Telescope is built around this idea, and it is one of the defining instruments of modern high-energy astronomy. It uses layers of dense converter material to trigger pair production, turning incoming gamma rays into electron-positron pairs. It then uses silicon trackers to record the paths of those particles as they pass through multiple layers. A calorimeter measures the energy deposited as the particles slow, multiply, and shower into secondary electrons and photons. Around the edges, an anti-coincidence detector helps reject charged particles that would otherwise mimic gamma events. From those tracks and energy deposits, we estimate direction and energy, but the process is never perfectly clean. The direction comes from extrapolating the pair's initial trajectories backward, while accounting for multiple scattering that blurs the path. The energy comes from the total shower in the calorimeter, corrected for leakage and geometry. The reconstruction is statistical, because every interaction is noisy, and because the detector has finite resolution. In practice, gamma-ray astronomy is a discipline of probabilities, where confidence grows with photon counts and careful modelling. In visuals, the detector becomes a kind of layered city. A gamma ray enters unseen, then suddenly becomes two bright lines that diverge and kink. Those lines leave tiny electronic signals in silicon strips, like footprints in snow. Deeper down, the calorimeter lights up with a compact cascade, a miniature storm of particles. Software then rewinds the event, turning debris into a direction on the sky. At somewhat lower energies, scintillators are common tools, and their simplicity hides elegant physics. A gamma ray deposits energy in a crystal or plastic that emits a flash of light. Photomultipliers or solid-state sensors convert that flash into an electrical signal. Timing and pulse shape helps separate gamma events from background particles, because different interactions produce different light profiles. For many missions, scintillators also serve as shields, vetoing events that arrive from the wrong direction. At the highest energies, above tens of GeV into TV, space telescopes become too small because the flux is low and the universe is stingy with the rarest photons. You need a vast collecting area to catch enough events for a meaningful spectrum. Here the atmosphere becomes a detector rather than an obstacle, and the ground becomes part of the instrument. A TV gamma ray initiates an air shower that moves faster than light travels in air, though not faster than light in vacuum. That distinction matters, and it is one of the most beautiful tricks in physics. That superluminal motion in air produces Cherenkov light, a brief blue flash that spreads in a thin cone. It is the optical equivalent of a sonic boom, created when charged particles outrun light's local speed in a medium. Imaging atmospheric Cherenkov telescopes capture that flash, with large mirrors and fast cameras. Arrays like HESS, MAGIC, and Veritas use multiple telescopes to triangulate the shower in 3 dimensions. The upcoming CTA will extend sensitivity and energy coverage with many telescopes, turning brief flashes into precise measurements. Direction is reconstructed from the shower image geometry and timing, because the elongated streak in the camera points back toward the source. Energy is inferred from the brightness and development of the shower, since more energetic primaries produce more particles and more light. Background rejection is crucial, because cosmic ray showers are far more common than gamma ray showers. The analysis separates gamma-like showers from hadronic ones using shape, timing, and stereoscopic consistency. Each accepted event is a small victory against noise. With these tools, the gamma ray sky becomes a map of extreme environments, not of ordinary heat. Gamma rays often trace particle acceleration, not thermal glow, so they highlight places where nature acts like a collider. They reveal where electrons and protons are pushed to relativistic speeds, carrying energies far beyond chemical processes. They also reveal where those particles collide with gas and radiation fields, converting motion into light. In a sense, gamma rays are the signatures of invisible engines. In the Milky Way, one major class of sources is pulsars, and their regularity contrasts with the chaos that made them. A pulsar is a rapidly rotating neutron star with a strong magnetic field, born in a supernova collapse. Its magnetosphere accelerates particles along field lines and creates beams of radiation that sweep the sky like lighthouse lamps. Many pulsars shine brightly in GeV gamma rays, with characteristic pulsed light curves. The pulse shapes encode geometry, because we see only the slices of the beam that cross Earth. The physics inside a pulsar magnetosphere is extreme, and it is still being refined. Electric fields can develop where plasma cannot fully screen the rotating magnetic field. Particles accelerate, emit curvature radiation, and trigger pair cascades that refill the magnetosphere with electrons and positrons. Those cascades can shape the gamma ray spectrum, producing cutoffs that Fermi can measure. Each pulsar becomes a test of electrodynamics under conditions we cannot reproduce on Earth. Magnetars are related but more extreme in magnetic field strength, and their behavior feels almost geological. Their fields can exceed 10^14 Gauss and stress the crust, storing energy like a twisted spring. Sudden rearrangements produce bursts and flares across X-rays and gamma rays, sometimes accompanied by quasi-periodic oscillations. They are rare, but they demonstrate how magnetic energy can become high-energy photons. When a magnetar flares, the sky briefly contains a new kind of sun. Supernova remnants are another central source class, and they are often described as laboratories for cosmic ray acceleration. A supernova blast wave drives a shock into surrounding gas, compressing and heating it. Shocks accelerate particles through diffusive shock acceleration, producing power law energy distributions that match what we infer for cosmic rays. The long-standing question is whether these remnants supply most galactic cosmic rays up to the knee. Gamma rays give us a way to test that claim with direct tracers. Gamma rays help test that question by tracing hadronic and leptonic processes, which can look similar at first glance. If accelerated protons hit gas, they produce neutral pions that decay into gamma rays. If accelerated electrons dominate, they can produce gamma rays by inverse Compton scattering or bremsstrahlung. Spectral shapes, energy cutoffs, and spatial correlation with gas help distinguish these channels. The difference matters because it tells us whether the remnant is accelerating mostly nuclei or mostly electrons. Some remnants show shell-like gamma ray morphology that matches shock fronts, like glowing rings drawn on the sky. Others brighten where the shock hits dense molecular clouds, and the contrast can be dramatic. Those cloud interactions increase target density and boost pion production, making the gamma rays a tracer of both acceleration and environment. In those regions, the remnant is not just a blast wave, it is a negotiation between shock physics and the structure of the interstellar medium. Binary systems add another layer of complexity, because geometry changes with time and the sky becomes variable. In gamma-ray binaries, a compact object orbits a massive star with a strong wind. The wind collision region can accelerate particles and create variable gamma emission, sometimes peaking at specific orbital phases. Orbital modulation reveals geometry, absorption, and changing target photon fields. The system becomes a moving experiment, repeating its cycle like a clock with a turbulent face. Microquasars, with jets launched by accreting black holes or neutron stars, can also emit gamma rays, and they echo the physics of distant quasars. Their jets accelerate particles and interact with surrounding radiation and matter, producing high-energy emission that can flare. These systems are laboratories for jet physics on smaller scales than active galaxies, where timescales are humanly observable. They also show how compact objects can shape their local high-energy environment. In gamma rays, even a small system can cast a long shadow. The galactic center region is a dense knot of sources and diffuse emission, and it challenges every attempt at a simple explanation. It contains the supermassive black hole SGR-A, massive star clusters, and complex gas structures threaded by magnetic fields. Gamma rays from this region are hard to interpret because many components overlap along the same lines of sight. Yet the center is a key testbed for cosmic ray transport and potential past outbursts. It is the closest place where we can study a galactic nucleus in detail. Some emission near the centre is consistent with a high density of unresolved point sources, too faint to separate individually. Millisecond pulses could contribute a significant fraction in certain bands, and their collective glow can mimic diffuse emission. Other emission traces dense gas in the central molecular zone, where cosmic rays have abundant targets. The region also hosts strong magnetic fields and turbulent conditions that change particle propagation. In that environment, even the definition of background becomes complicated. Beyond discrete sources, the Milky Way glows diffusely in gamma rays, and that glow is one of the most informative signals we have. This diffuse glow is not a background nuisance, but a physical map of cosmic rays interacting with the interstellar medium. Cosmic rays fill the galaxy and collide with gas almost everywhere, even where there are no obvious accelerators. Those collisions create gamma rays that trace both cosmic ray density and gas distribution. The result is a kind of high-energy weather map of the entire disk. The most direct channel is pion production, and it has a distinctive fingerprint. A cosmic ray proton hits a gas nucleus and produces a shower of particles, including neutral pions. Neutral pions form and quickly decay into two gamma rays, leaving a characteristic spectral bump. That bump is a signature of hadronic interactions, a clue that protons and nuclei are doing the work. When we see it, we are seeing the galaxy's particle collisions written in light. This mechanism ties gamma rays to the vertical structure of the galaxy, because gas is not distributed evenly with height. Gas density is highest near the midplane and falls with altitude, in layers shaped by gravity and feedback. If cosmic rays were confined strictly to the plane, high-latitude gamma rays would be weak. The observed high-latitude glow implies cosmic rays permeate thick disk and halo volumes. That implication forces models of diffusion, convection, and magnetic trapping to match the sky. A second diffuse channel is inverse Compton scattering, which turns low-energy light into high-energy light through collisions with relativistic electrons. Relativistic electrons collide with low-energy photons and boost them to gamma-ray energies. The target photons come from starlight, infrared dust emission, and the cosmic microwave background. Because the CMB is everywhere, inverse Compton can remain important even far from the plane. In plain terms, electrons can turn the universe's faint glow into something fierce. Inverse Compton emission becomes a tracer of electron populations and radiation fields, and it also becomes a tracer of height. The starlight field drops with distance from the disk, while the CMB remains constant, so the balance changes as you move upward. The balance between pion decay and inverse Compton changes with latitude, and that balance encodes how cosmic rays propagate and lose energy. Electrons cool by radiating, so their spectra steepen with time and distance. When we map inverse Compton, we are mapping both motion and aging. Bremsstrahlung adds another contribution when electrons interact with gas, radiating as they are deflected by electric fields of nuclei. It is strongest where gas density is high, so it tends to follow the plane and dense clouds. At high latitudes, it usually fades faster than inverse Compton because the gas thins out. Separating these components requires models of gas, radiation fields, and cosmic ray spectra. It also requires humility, because uncertainties in any template can masquerade as new phenomena. These diffuse processes make gamma-ray maps into a kind of tomography, where different energies probe different mechanisms. Gas traced by radiohydrogen and CO surveys becomes a template for pion emission, though conversion factors and hidden phases complicate the picture. Dust maps help correct for gas not seen in CO, often called dark gas, which still provides targets for collisions. Radiation field models help predict inverse Compton intensity, and those models depend on stellar populations and dust absorption. The comparison between predictions and observations tests our understanding of the galaxy's vertical ecosystem. When the fit fails, it is an invitation to learn. One structure forces itself into this discussion because it is literally above and below the galactic center, like a pair of luminous lungs. The Fermi bubbles are giant lobes extending tens of thousands of light-years north and south of the plane. They were discovered as large, hard-spectrum gamma-ray features that stand out against the softer, diffuse glow. Their edges are relatively sharp, suggesting a distinct event or sustained outflow rather than a gradual gradient. In silhouette, they look like boundaries drawn with intent. The discovery itself is part of the modern story, because it depended on full-sky surveys and careful subtraction. Fermi's all-sky view revealed patterns that older instruments could not see clearly. Once point sources and known diffuse components were modelled, the residual structure remained: 2 vast lobes. The bubbles were not predicted in their final form, which is why they felt like a reveal. They reminded us that the galaxy still has surprises, even in our own backyard. The bubbles connect to earlier ideas of chimneys and fountains, but at much larger scale, and they force a reassessment of how the disk vents energy. They imply that energy was injected near the galactic centre and transported vertically, punching into the halo. They also imply that cosmic rays and magnetic fields can fill enormous volumes, not just the thin disk. In the language of this documentary, they are a visible architecture of above and below. They make the halo feel inhabited. Their origin is still debated, and the competing scenarios are instructive rather than frustrating. One possibility is past AGN-like activity from Sirius, when accretion briefly turned the black hole into a more active engine. Even a modest accretion episode could launch jets or winds that inflate lobes and accelerate particles. Another possibility is a nuclear starburst that drove a sustained wind from clustered supernovae and massive stellar feedback. Both scenarios are plausible, and both would leave multi-wavelength echoes. Both scenarios require energy and timescales that can be compared with observations, and that comparison is where the science lives. The gamma-ray spectrum suggests either hadronic cosmic rays interacting with low-density gas, or leptonic electrons producing inverse Compton gamma rays. Microwave haze and polarized radio structures provide additional clues about electrons and magnetic fields, hinting at synchrotron emission. X-ray features suggest hot gas boundaries that may trace shocks or contact discontinuities. Each band adds a layer, and the combined picture is still being assembled. The bubbles also matter because they intersect the question of cosmic ray confinement, which is central to the galaxy's high-energy ecology. If cosmic rays are trapped in these lobes, they can persist and radiate for long times, making the bubbles a kind of reservoir. If they escape quickly, the bubbles must be continuously powered, implying ongoing injection. Either way, the structure implies vertical transport that is not uniform across the galaxy. It suggests that the disk and halo exchange matter and energy through channels, not through a gentle seep. From the Milky Way, we push outward to the high-energy universe beyond it, where gamma rays become beacons across intergalactic space. Gamma rays travel in straight lines, so they can point back to distant engines with a clarity cosmic rays cannot match. Yet the universe is not fully transparent to the highest energy gamma rays, and that opacity is itself a measurement. Interactions with the extragalactic background light can absorb TV photons over long distances. In effect, the cosmos has a horizon for the hardest light. The brightest persistent extragalactic gamma ray sources are blazars, and their appearance is shaped by orientation. A blazar is an active galaxy with a relativistic jet pointed near our line of sight. Beaming makes the emission appear much brighter and more variable, because relativistic motion concentrates photons forward. The jet accelerates particles and produces gamma rays through inverse Compton and possibly hadronic processes. When a blazar flares, it can outshine its entire host galaxy in gamma rays. Blazar variability reveals compact emission regions and extreme conditions because light travel time sets a limit on source size. Flares can rise and fall in hours to days, implying small regions embedded within a jet that spans light years. Spectral breaks can indicate absorption, cooling, or changes in particle acceleration, and sometimes they hint at internal photon fields. Because blazars are numerous, they contribute significantly to the extragalactic gamma-ray background. That background is not just noise, it is the integrated glow of countless distant engines. Gamma-ray bursts are the most dramatic transient sources, and their brevity is part of their mystery. They appear as brief flashes, lasting from milliseconds to minutes, followed by fading afterglows at lower energies. They are divided into long and short classes with different progenitors, a classification that emerged from decades of observations. Long GRBs are linked to the collapse of massive stars, while short GRBs are linked to compact object mergers. In both cases, the central engine launches an ultra-relativistic jet. Beaming is central to GRBs and to risk assessment, because it changes both what we see and what we fear. The emission is not isotropic, but concentrated into narrow jets with opening angles that can be only a few degrees. We only see a fraction of all GRBs because most jets do not point at us. This selection effect means observed rates underestimate true rates, while the danger to any one planet depends on jet orientation. The universe can be full of explosions, yet most never touch us. Distance is the other protective factor, and it is often the decisive one. Most GRBs occur at cosmological distances billions of light-years away, where their photons arrive as a faint but detectable signal. Their gamma rays reach us as data, not as hazard, because the energy flux is too low to harm Earth. Even within the Milky Way, GRBs are rare and a dangerous alignment would be exceptional. The sky is powerful, but it is also large. Still, the documentary's visceral claim deserves careful framing, because the physics of harm is real even when the probability is low. Gamma rays are deadly in principle, but catastrophe requires proximity, direction, and sufficient energy delivered to the atmosphere. The main plausible biospheric mechanism is ozone depletion, not instant incineration. High-energy photons and secondary particles can dissociate nitrogen and oxygen, producing NOx that catalytically destroys ozone. The chemistry is subtle, but the consequences can be broad. Ozone loss increases ultraviolet radiation at the surface, stressing ecosystems and altering atmospheric chemistry over months to years. The severity depends on fluence, spectrum, and duration, and also on the season and latitude of irradiation. A nearby supernova could also contribute through cosmic rays arriving over longer times, extending the period of atmospheric ionization. The danger is not a single flash only, but a sustained change in the protective chemistry of the sky. In that scenario, sunlight becomes the secondary threat. What counts as nearby depends on the event, and the thresholds are uncertain enough to demand careful language. A core collapse supernova within tens of light-years could be damaging, though uncertainties remain in cosmic ray transport and atmospheric response. A GRB within the Milky Way, pointed at Earth within a few kiloparsecs, could be severe, especially if the spectrum is hard. These are not everyday threats, but they are not physically impossible. The question is not whether nature can do it, but how often it does. Probability matters, and it must be stated without drama, because risk is a combination of severity and frequency. Supernovae occur in the Milky Way a few times per century, but most are far away and heavily obscured by dust. Nearby supernovae within a few tens of parsecs are rare on human timescales, perhaps once per many millions of years. GRBs in our galaxy are rarer still, and beaming reduces the chance of a direct hit. The sky's most dangerous events are also the least likely to target us. Evidence matters too, because risk claims must be anchored to data rather than to imagination. Geological and chemical proxies can record unusual atmospheric ionization, but each proxy has caveats. Nitrate spikes in ice cores have been proposed, though interpretation is contested and confounded by terrestrial processes. Cosmogenic isotopes like carbon-14 and beryllium-10 can reflect changes in cosmic ray flux, but solar variability complicates attribution. The record is real, yet it is noisy, and the challenge is separating signal from weather and climate. For supernovae, isotopic evidence is stronger in principle, because it can carry a fingerprint of stellar nuclear synthesis. Iron-60 in ocean sediments indicates nearby explosions within the last few million years, and its half-life makes it a useful clock. That signal implies Earth has been within reach of supernova ejecta, even if biological impact was limited. It also implies our local environment is shaped by stellar deaths, not only by slow galactic drift. The solar system moves through a landscape that has been recently disturbed. A careful narrative distinguishes detection from hazard, because the same phenomenon can be dramatic in one sense and harmless in another. A supernova can be close enough to deposit isotopes without causing mass extinction, depending on distance and atmospheric response. A GRB can be detected from across the universe without any local effect, because the inverse square law is unforgiving. The high-energy sky is dangerous in capability, but usually distant in practice. That balance is the honest source of awe. This balance brings us back to the central question about what exists above and below, because high-energy radiation is not uniformly distributed. It is shaped by the galaxy's vertical structure, and it changes as environments change. Gas density, radiation fields, and magnetic confinement all vary with height above the plane. The result is a changing gamma-ray environment as the solar system moves through the Milky Way. Even if the sky looks the same to our eyes, the invisible sky does not. The sun's motion is not only around the galactic center, but also up and down through the plane, like a slow oscillation through a crowded disk. As it bobs, It samples different gas densities and different cosmic ray transport conditions. Near the midplane, there are more supernova remnants and more dense targets for collisions, so diffuse emission tends to be brighter. Farther from the plane, there is less gas but potentially different confinement and background components. The vertical journey changes the balance of interactions. The heliosphere adds another filter, but it cannot stop gamma rays, and that limitation clarifies the difference between photons and particles. It modulates lower energy charged cosmic rays, and its size depends on external pressure from the surrounding interstellar medium. When the solar system moves through denser clouds, the heliosphere can compress and change cosmic ray access to the inner planets. Gamma rays bypass that filter, so their variability is dominated by external sources and line-of-sight geometry. The sky's hardest light is indifferent to the sun's magnetic bubble. Even when gamma rays do not strike us directly, cosmic rays do, and they are linked to gamma rays by shared origins and shared physics. Cosmic rays are charged particles, mostly protons and nuclei, accelerated by shocks and other engines across the galaxy. They are deflected by magnetic fields, so their arrival directions are scrambled, and their sources are hard to pinpoint. Gamma rays, by contrast, point back, so they help identify where cosmic rays are made. In that way, gamma rays become the map, and cosmic rays become the weather. This is why the diffuse gamma ray glow is so important, and why it is not merely a backdrop to the brighter sources. It is a tracer of cosmic ray density integrated through the galaxy's gas, averaged over vast distances. It tells us that cosmic rays fill a thick volume around the disk, not a thin sheet, and that they leak into the halo. It also tells us that above and below are active regions where particles propagate, collide, and radiate. The halo is not empty space. It is a medium with energy moving through it. The Fermi bubbles sharpen that lesson into a single silhouette, and they do it with an almost architectural clarity. They show that the galactic center can drive vertical structures on halo scales, reaching far beyond the star-forming disk. They show that the high-energy sky contains fossils of past outbursts, preserved as large-scale emission. They also show that the boundary between disk and halo is not quiet, but a channel for energy and particles. When we look above and below the plane, we see the galaxy breathing, so the paradox resolves into a better question. If radiation is the message from above, what is the force that moves us through the message? If the sky can harm us, what shapes the paths that bring us under different skies? The answer is not only in explosions and jets, it is also in motion, and motion is governed by gravity. Radiation is only half the story. Even when nothing hits us, something still pulls us. To understand the hidden below, we must follow the gravity that moves the sun like a leaf in a current. That current carries us through layers of gas, fields, and history, and it quietly sets the stage for everything above. Radiation is only half the story. Even when nothing hits us, something still pulls us. Gravity is the quiet architecture under every layer we mapped, and it never switches off. Not in vacuum, not in darkness, not even between the stars. It sets the galaxy's shape, sets our orbit, and sets what above and below can even mean when there is no true up. The solar system is not parked in space, and it is not merely travelling in a straight line. It rides inside the Milky Way's rotating disk, carried by a gravitational current we feel only through motion and through the subtle accelerations that keep us bound. On screen, the Milky Way is a luminous pinwheel, but the light is only the surface. Beneath the glow is a mass distribution that acts like a sculpted landscape, valleys, slopes, and basins, guiding every orbit whether we see the guide or not. Start with the simplest fact, because the simplest fact already sounds unreal. The Sun orbits the galactic center at roughly 220 to 240 kilometers per second, fast enough to cross the United States in under 20 seconds. That speed is not measured by watching the Sun crawl against the constellations, because from inside the disk we share the motion. It is inferred from how stars and gas rotate around the center, and from our own local kinematics stitched together into a coherent rotation curve. Astronomers use several interlocking methods, and each one is a different kind of ruler. They track Doppler shifts in spectral lines from hydrogen gas. They measure proper motions of masses in star-forming regions, and they compare stellar velocities to models of galactic rotation. In practice, those masses act like cosmic survey stakes, bright compact beacons whose positions can be triangulated across Earth's orbit. With very long baseline interferometry, their tiny annual parallax becomes measurable, and their sideways drift becomes a clock for galactic rotation. Even the number itself carries a history of refinement. Early estimates depended on uncertain distances and sparse samples, but radio astronomy and modern astrometry turned the Milky Way into a measurable machine, one where speed can be deduced from geometry and timing. There is also a deeper reason the measurement is hard. We are embedded in the disk's dust and crowding, looking through a cluttered city to infer the city's shape. Extinction dims distant traces, confusion blends stars together, and yet the rotation still emerges from the statistics. At that speed, one circuit takes on the order of 200 to 250 million years, depending on the exact radius and the adopted rotation model. A single galactic year is longer than complex life's entire history on Earth, and it dwarfs the span of human memory into a thin, forgettable line. If we could compress time, we would see the sun sliding around the centre like a bead on a spinning record. But the record is warped, thick and alive with structure, so the bead does not trace a perfect ring. Yet the orbit is not a perfect circle traced on a flat sheet. The Milky Way is a three-dimensional potential, and the sun's path is a braided motion, combining circular rotation with smaller oscillations and slow drifts. In a clean textbook, a star follows a closed ellipse around a point mass. In a real galaxy, mass is spread out in a disk, a bulge, a bar, and a halo, so the orbit becomes a rosette that precesses rather than repeating. That precession is not just a mathematical flourish, it is the signature of distributed mass, because different radii want to orbit at different rates. Over long times, those mismatched rates shear patterns, mix stellar neighbourhoods, and slowly erase the memory of where a star was born. Astronomers define a reference flow called the local standard of rest, a kind of averaged conveyor belt for our neighbourhood. It is the mean circular motion of nearby stars in the disk at our radius, smoothed over random stellar motions. The local standard of rest is not a physical object, and it is not a rigid frame painted onto space. It is a statistical idea, useful because it gives us a baseline for what typical rotation looks like near the Sun. Relative to that flow, the Sun has a peculiar motion. We drift a little faster or slower than the local mean, and we move slightly inward or outward, and we also carry a vertical component that points us away from the plane. That peculiar motion is small compared with the main rotation, but it is not negligible. It changes our relative speed through nearby gas, through stellar neighbourhoods, and through magnetic turbulence that fills the interstellar medium. On screen you can visualize it as a gentle offset arrow laid on top of a much larger circular arrow, our private drift riding on a public current. In velocity space it is a small displacement, but it changes which material we overtake and which material overtakes us. It also matters for interpreting messengers from Chapter 4, because motion changes what we measure. A moving observer sees different anisotropies in cosmic rays, and different Doppler patterns in gas and dust, and even subtle shifts in the apparent direction of incoming particles. When we say cosmic ray anisotropy, we mean a tiny imbalance in arrival directions, often at the level of parts per thousand or less. Those small imbalances can be shaped by local magnetic fields, but they are also shaped by our own motion through the medium. Even the simplest expectation, the Compton-Getting effect, predicts a dipole-like anisotropy from motion alone, as if the sky was slightly brighter in the direction we move. The real sky is more complicated, which is precisely why the baseline matters. So the paradox resolves into a better question. If gravity is the current, what is the shape of the riverbed? The next piece is vertical, and it is easy to miss because the sky looks flat from the ground. The sun does not stay at a fixed height above the galactic midplane, even though the disk's bright band makes that plane feel permanent. Disk gravity pulls toward the plane, while vertical velocity carries us through it, and the two together create a slow oscillation. The result is a gentle bobbing through the densest layer, like a buoy rising and falling on a long, deep swell. Visually, imagine the Milky Way's disk as a thin, glowing fog bank, with darker lanes of dust cutting through it. Our solar system threads up and down through that fog, sometimes closer to the crowded midplane, sometimes drifting into clearer, thinner regions. In wide shots, the plane looks like a bright seam stitched across the sky, but the seam has thickness and texture. Star clouds brighten it in patches, dust lanes bite into it, and the whole band hints at a gravitational midline we cannot see. The period is model-dependent, but it is commonly placed around 60 to 90 million years, with different studies landing at different points. the uncertainty is not ignorance of motion, but uncertainty in the local mass distribution that supplies the restoring force. The amplitude matters as much as the period, because it sets how far we wander from the dense layer. Estimates vary, but the Sun's vertical excursion is often discussed in the range of tens of parsecs, which is modest compared with the galaxy's size yet significant for local density. To translate that, a parsec is about 3.26 light-years, so these are distances comparable to the spacing between stellar neighbours. We are not leaving the disk, but we are sampling measurably different layers of its gas, dust and radiation fields. We infer the oscillation from stellar kinematics, because stars near the plane behave like test particles in a gravitational well. Their vertical velocities and heights encode the restoring force of the local potential, and that force points to how much mass is present. In a simple approximation, the vertical force near the plane is proportional to height, at least over small distances. That makes the disk behave like a weak spring over small excursions, which is why the motion resembles a harmonic oscillator in first order. But the real galaxy is not a perfect harmonic oscillator, and it never truly sits still. Gas clouds, spiral structure, and past mergers create ripples, bending waves, and local asymmetries, so the spring constant changes with position and time. Gaia's maps make this vivid, because the disk shows coherent patterns in velocity, like a sheet that has been tapped and is still ringing. Those patterns are not random noise, they are the signatures of perturbations propagating through a self-gravitating system. Even so, the basic inference holds, and it is surprisingly robust. The Sun crosses denser regions near the midplane more often than it visits the sparse extremes, and that repeated crossing changes the background conditions we live inside. That changes the environment without needing dramatic events or rare catastrophes. Near the plane there is more gas, more dust, more massive stars, and more targets for cosmic ray collisions that produce secondary particles and gamma rays. Near the midplane, the interstellar medium is also more structured, with cold molecular clouds embedded in warmer atomic gas and threaded by magnetic fields. Those phases exchange energy through shocks, turbulence and radiation, and gravity helps hold the whole layered system together. Farther from the plane there is less neutral gas, different ionization conditions, and often a clearer view in many wavelengths, because dust extinction drops. The vertical journey changes both exposure and interpretation, and it changes which parts of the galaxy are easiest to observe. The vertical motion also links to the earlier detector volume idea, because our line of sight through the galaxy changes with height. The halo and thick disk are not empty, and our changing height changes the column we sample. How much material lies between us and distant sources. If you picture a flashlight beam cutting through fog, the brightness you see depends on how much fog the beam crosses. In astronomy, gravity shapes the fog's distribution, and our orbit decides how much of it lies in front of us. To turn that into numbers, astronomers measure the local gravitational field rather than guessing it. They do it by treating stars as test particles in a potential, then asking what mass distribution makes their motions make sense. The classic approach is associated with the Oort limit, named after Jan Oort, who helped transform the Milky Way from a mythic band into a dynamical system. It constrains the total mass density near the midplane from the vertical motions of stars, using the logic of equilibrium. Oort worked in an era when the galaxy structure was still debated, and when spiral nebulae had only recently been recognized as other galaxies. In that context, weighing our own disk from inside it was an audacious kind of astronomy, more mechanics than photography. The logic is direct, and it is almost mechanical in its simplicity. If stars have a certain vertical velocity dispersion, then a certain gravitational pull is required to keep them bound near the plane. Otherwise, they would drift away and the disk would puff up. You count stars as a function of height, and you measure their vertical velocities, and then you solve for the mass density that produces the observed distribution. In practice, you also account for how the stellar population changes with height, because young and old stars do not share the same kinematic temperature. This is not a single measurement, but a chain of assumptions that must be made explicit. You must model selection effects, distances, binaries, and the fact that different stellar populations have different dispersions, and you must decide how close the system is to equilibrium. Distance is especially treacherous, because a small error in distance becomes a larger error in height above the plane. Before precise parallaxes, the vertical density profile could be blurred by uncertainty, and that blur would masquerade as extra mass or missing mass. You also must separate visible mass from total mass, because gravity does not label its sources. Visible mass includes stars, stellar remnants, and gas in multiple phases, including molecular, atomic, and ionized components, each traced by different observations. Molecular gas is often inferred from carbon monoxide emission, but that inference requires a conversion factor that can vary with environment. Atomic gas is traced by the 21 centimeter line of neutral hydrogen, while ionized gas can be traced by emission measures and dispersion measures, each with their own uncertainties. Historically, uncertainties in gas and faint stars left room for missing local mass, and the accounting did not close cleanly. That gap was one of the early hints that not all gravitating matter is luminous, even though the modern dark matter story was built first on galactic rotation. It is worth remembering how radical that idea once was, because it was not born from a single dramatic discovery. It grew from a pattern of mismatches, motions that were too fast, systems that were too stable, and gravitational pulls that seemed too strong for the light we could count. Modern astrometry tightened the problem, and it did so with an almost cinematic leap in precision. Gaia measured positions, parallaxes, and proper motions for more than 1 billion stars, turning the local disk into a living map of trajectories. Gaia turns the local disk into a phase space map, meaning we can place stars in both position and velocity, not just on the sky. It lets us measure vertical waves, moving groups, and the detailed shape of the vertical potential, because the data are dense enough to reveal subtle structure. On screen this looks like a cloud of points, but the cloud has filaments and ridges. Those ridges are the fossil record of dynamical processes, resonances, perturbations, and the slow mixing of orbits over time. Gaia also reveals that the disk is not in perfect equilibrium, and that matters for any method that assumes it is. There are bending and breathing modes, likely excited by satellite interactions and internal structure, and they show up as coherent patterns in vertical velocity. That complicates the simplest ought-limit analysis, because equilibrium equations can misread a ringing disk as extra mass. Yet it also adds information, because disequilibria carry signatures of the underlying mass distribution and of the events that disturbed it. When we combine Gaia kinematics with star counts and gas maps, we can estimate the local mass density more robustly, even if the disk is not perfectly settled. We can ask how much is baryons and how much is something else, and we can put error bars on the answer. This is where above and below becomes literal in gravity, not just poetic. The vertical pull near the plane comes from matter in the disk, plus matter in a more extended component that does not thin out quickly with height. That extended component is the dark matter halo, and it is the dominant mass component above and below the disk on large scales. It is not a thin layer you can point to on the sky, but a three-dimensional envelope that surrounds the luminous galaxy. Dark matter enters the story not as a guess, but as an inference from motion, repeated across many systems. The most famous evidence comes from flat rotation curves, measured first in external galaxies where the geometry is easier to interpret. If most mass were in the visible disk and bulge, orbital speeds would fall with radius, because gravity would weaken as you move away from the bright center. Instead, many galaxies show roughly constant rotation speeds far beyond their bright edges, where starlight fades into darkness. A flat curve implies enclosed mass keeps rising with radius, even where there is little light. That requires a large extended mass distribution that does not emit much light, and it must be arranged so its density declines slowly enough to keep speeds high. On screen, the rotation curve is a simple plot, yet it carries a quiet shock. The line refuses to drop. It is as if the galaxy's outskirts are riding an unseen rail, held up by mass that does not glow. The Milky Way shows the same basic pattern, even though measuring it from inside is harder. Gas and stars orbit faster than visible matter alone can support, especially in the outer galaxy, where the stellar disk thins and the bulge is far behind. So the galaxy sits inside a halo that extends far beyond the disk, and far beyond what the eye would call the Milky Way. The visible Milky Way is a bright island inside a much larger gravitational basin, and we live deep within that basin's slope. The halo is not a boundary you cross like a wall, and it does not announce itself with a change in scenery. It is a gradual dominance of invisible mass, and its presence is felt as the background curvature of the galactic potential. That changes how we interpret below, because below the solar system is not only the disk mid-plane. Below is also the deeper potential well of the halo that surrounds us, pulling from every direction with a force that is smooth in average, and uncertain in detail, dark matter also reframes the central question, and it does so with a quiet audacity. What exists above and below the solar system is not only gas and plasma, but a dominant mass component we cannot see, and yet we can weigh. Yet the halo is not fully characterized, and the unknowns are not minor technicalities. Its density profile, its shape, and its substructure remain active frontiers, because each one changes predictions we can test. Start with shape, because shape is geometry turned into dynamics. A halo can be oblate, prolate, or triaxial, depending on its formation and on how baryons settled into the disk, and those shapes change how orbits precess over time. A flattened halo changes orbital families and changes precession rates, subtly twisting the paths of stars and streams. It also changes the vertical restoring force and the sun's long-term trajectory through the disk, because the pull toward the plane depends on the full mass distribution. Halo shape matters for local dark matter density, and that density sets expected event rates in direct detection experiments on Earth. If the local density is higher, more particles pass through a detector each second, and the odds of a rare interaction rise. It also matters for annual modulation signals, which rely on the Earth's changing velocity through the halo. The Earth moves around the Sun, and the Sun moves through the halo, so the relative wind of dark matter depends on halo kinematics and on our own peculiar motion. The local standard of rest appears again here, because it provides a baseline for the Sun's motion through the galaxy. The expected dark matter wind is often modelled relative to the LSR, plus the Sun's peculiar motion, producing a preferred incoming direction in the simplest models. But the halo may not be a simple, smooth, isotropic distribution, and the Milky Way's history suggests it should not be. It may have streams, debris flows, and anisotropies left from mergers, because galaxies grow by accretion, and the debris does not instantly thermalize. Those features can change the velocity distribution at Earth, even if the average density stays the same. Two models with the same mean density can predict different recoil spectra in detectors, because the high velocity tail and directional structure matter. So the halo is not only a global structure described in textbooks, it is a local experimental parameter, and our ignorance becomes an uncertainty budget in the lab, one that can blur the meaning of a null result or a tentative signal. How do we measure halo properties if it does not shine, and if it refuses to reveal itself directly? We use gravity again, but now on larger scales, and we accept that every measurement is a triangulation rather than a single photograph. We use the Milky Way's rotation curve, but also the motions of satellite galaxies and globular clusters, which orbit far into the halo. We use stellar streams as long, fragile test particles, because their shapes preserve a memory of the forces that acted on them. A stellar stream is the stretched remnant of a disrupted cluster, or dwarf galaxy, pulled apart by tides and laid out along an orbit. Its path traces the gravitational potential it moves through, and its thickness and gaps reveal how smooth that potential is. If the halo is smooth, streams are thin and coherent, like pencil lines across the sky. If the halo is lumpy, streams are perturbed, heated, and sometimes split, and the disruptions can be read as evidence for unseen masses. In visual terms, a stream can look like a faint brushstroke, barely brighter than the background, yet geometrically precise. When that brushstroke kinks or frays, the distortion becomes a clue, an imprint left by something that never lit up. Subhalos are a key prediction of cold dark matter, and they emerge naturally from hierarchical structure formation. The halo should contain many smaller clumps, most of them too small to form stars, making them effectively invisible except through gravity. We cannot see those dark subhalos directly, so we look for their gravitational fingerprints. We search for stream gaps, stream wiggles, and unexpected velocity kicks, and we compare the patterns to simulations that include different subhalo populations. This is detective work done with geometry, and it demands patience. A gap in a stream could be a subhalo encounter, but it could also be observational incompleteness or a complex progenitor history. So the case is built by consistency across multiple streams. We also look for relics of mergers in phase space, where stars from an accreted galaxy can remain clustered in velocity even after they spread across the sky. Gaia revealed that the local halo contains debris from past accretion events, mixed but not erased, like dye stirred into water but not fully dissolved. Those mergers matter for the halo's present structure, because each accretion event deposits both stars and dark matter. Each one can add streams of dark matter as well as streams of stars, and the two need not align with the disk's rotation. So the halo may contain dark streams that do not align with the disk, and may even pass through the solar neighbourhood. If so, the solar system's motion through the halo is not through a uniform fluid, but through a medium with currents and eddies. This brings tension back into the narrative because we are trying to describe something we cannot photograph. We can measure the average field, but we may be missing the fine grain, and fine grain is where rare effects can hide. Is the halo smooth enough that only averages matter for our local environment and for our detectors? Or is it clumpy enough that the solar system sometimes passes through subtle overdensities, changing local density by a few percent or more? Even small perturbations can matter over long times because gravity integrates. The solar system's outer reservoirs are sensitive, and the cumulative effect of weak tugs can become visible only after millions of years. The Oort cloud is the key example, and it is almost designed to be sensitive to whispers. It is a vast population of icy bodies on weakly bound orbits, far beyond the planets, stretching perhaps tens of thousands of astronomical units from the Sun. Because those orbits are weakly bound, the Oort cloud is a gravity antenna tuned to low-frequency disturbances. Tiny tugs can change perihelia, turning distant bodies into inbound comets, and a small change in angular momentum can decide whether an object stays remote or visits the inner system. On screen, the cloud is often drawn as a pale sphere, but the reality is more like a sparse swarm, countless small bodies separated by enormous distances. In that emptiness, a gentle tidal twist can be more important than a dramatic shove. Some tugs are obvious, and they have names and trajectories we can model. Passing stars can perturb comet orbits, especially when a star passes within a fraction of a parsec, and the encounter geometry determines whether comets are injected or stabilized. In the deep time view, even a modest star can matter if it passes close enough because the Oort cloud is so extended. The Sun's birth cluster likely produced early encounters, and later the solar system drifted into a quieter field, though never a perfectly quiet one. Molecular clouds can do the same, with even larger mass and extended gravitational influence, and their effect can be strong even at larger distances. Encounters are rare, but the consequences can be long-lived, because a single passage can reshape the distribution of comet orbits. There is also the galactic tide, which is not a single object but a field. The combined gravitational field of the disk and halo exerts a differential pull across the Oort cloud, because the cloud is large enough that down is slightly different at its far edge. That tide can slowly torque comet orbits, and it does so continuously rather than in a single moment. It can lift perihelia or lower them, feeding a trickle of long-period comets into the inner solar system, where they become visible only in their final brief arc. The tide depends on local mass density and on our height above the plane, because the vertical component of the galactic field changes with z. Vertical oscillation changes the tide's strength and direction over time, so the injection rate can be modulated even without any close encounter. This is where below reaches into the solar system without touching it, and without leaving a crater as proof. The planets may be stable, yet the comet reservoir can be stirred, and the stirring can change the statistical background of impacts and close passes. The idea has tempted dramatic claims about periodic impacts, because a periodic vertical motion suggests a periodic forcing. The evidence for strict periodicity is weak, but the mechanism for modulation is real, and it invites careful, skeptical analysis. A midplane crossing does not guarantee catastrophe, and it does not flip a switch from safe to dangerous. It changes probabilities by changing the density of perturbers and the strength of the tide, and probability is the language of rare events. The same is true for spiral structure, which is part of the disk's mass pattern and part of its star formation engine. Spiral arms concentrate gas and star formation, which can raise encounter rates with clouds and increase nearby supernova probability, even if the arm is a broad fuzzy region. But spiral arms are patterns, not rigid walls, and their nature complicates any attempt at precise scheduling. Their positions and speeds are uncertain enough that precise timing is difficult over hundreds of millions of years, especially when the Sun's own orbit is not perfectly circular. So we keep the stakes grounded because the story is subtle rather than apocalyptic. Gravity does not write a simple schedule, but it does shape the long-term background risk landscape, nudging the odds rather than dictating outcomes. Dark matter substructure adds a speculative layer, but it is a speculation constrained by theory and observation. A dense subhalo passing near the solar system could, in principle, perturb the Oort cloud, because gravity does not care whether the mass is luminous. The probability and expected strength are uncertain, and that uncertainty is part of the scientific tension. The question is not whether gravity can do it, but how often such close passages occur, and whether the distribution of subhalo masses allows strong encounters in the solar neighbourhood. Streams are another possibility, and they are conceptually different from compact clumps. If the solar system moves through a dark stream, local density and velocity distribution could change for a time, altering the wind seen by detectors and slightly changing the local gravitational environment. That would matter most for experiments on Earth, and for any subtle gravitational effects on the outer solar system, though the latter would likely be extremely small. It would be a quiet crossing, not a visible event, and its evidence would be statistical rather than cinematic. We can search for indirect hints, because the halo's invisible structure should leave visible echoes. If stream perturbations shape stellar streams, they might also shape dark streams, and both would trace the same merger history, different traces of the same gravitational past. We can also compare independent constraints because gravity can be measured from multiple directions. Local density from vertical kinematics must be consistent with global halo models from rotation and satellites, and inconsistencies can reveal missing physics or missing systematics. This is the documentary's method in miniature, and it is also the discipline of modern astrophysics. We do not trust one messenger, and we do not trust one dataset. We cross-check gravity with gravity, and we look for consistency across scales. Now we connect back to the earlier chapters, because the themes are braided like the sun's orbit. The halo was a detector volume for radiation and particles, but it is also a mass reservoir that sets trajectories and defines what paths are even available. Magnetic fields scramble cosmic rays, but gravity sets where the gas sits that cosmic rays collide with, and where shocks can form. Radiation maps the energetic layer, but gravity maps the container, and the container shapes the map. So the central question sharpens, and it becomes harder to answer with a simple picture. What exists above and below the solar system is not only matter we can map in emission, but mass we infer from motion, and motion is measured with exquisite care. And motion is the only direct language dark matter speaks, at least so far. It shapes rotation curves, sculpts streams, and sets the vertical pull that makes the sun bob, and it does so without emitting a single photon we can capture. We can describe the local potential with increasing precision, yet the global halo remains uncertain in its fine structure, and that uncertainty is not cosmetic. It changes predictions, and it changes how confident we can be when we interpret a measurement. It changes how we interpret stream gaps, because a gap could be a subhalo or a different dynamical effect. It changes how we design detection experiments, because detector thresholds and target materials respond differently to different velocity distributions. It changes how we estimate long-term perturbations of comet reservoirs, because the tide depends on mass density, and the encounter rate depends on where we travel. The invisible current beneath is therefore not a metaphor but a measurable field with unknown texture. Next, we treat the halo not as emptiness, but as a gravitational medium with weather. We ask whether its clumps and streams leave signatures we can actually test, and whether those tests can distinguish between a smooth sea and a structured flow. The solar system's drift is only one chapter in a larger motion, and the scale keeps expanding. The Milky Way itself is moving through a still larger gravitational landscape, pulled by nearby galaxies and the mass of the local group. Gravity moves us through the galaxy, but the galaxy is moving through something larger. To find what lies above and below in the grandest sense, we must zoom out beyond the Milky Way and follow the same invisible logic into intergalactic space. Gravity moves us through the galaxy, but the galaxy is moving through something larger, and that larger motion leaves signatures we can actually measure. The frame widens until above and below stop being directions on a sky grid, and instead become directions in a flow field, set by mass we barely see, and by expansion we can't feel. Begin with our nearest scale beyond the Milky Way, where the familiar starfields thin into a sparse three-dimensional archipelago. The sun rides inside a galaxy that is not alone, not isolated, and not dynamically quiet, because even our nearest neighbours tug and respond. The Milky Way and Andromeda dominate a small swarm called the Local Group, a collection spanning a few million light-years. Around them orbit dozens of satellite galaxies, plus faint dwarfs still being discovered in deep, wide-field surveys that push down to extremely low surface brightness. On screen, the Milky Way is no longer a band of light but a halo-draped disk, surrounded by dim companions like embers around a fire. Some satellites are compact spheroidals with little gas, their star formation mostly shut down by stripping and exhaustion. Others are ragged, gas-rich dwarfs whose star formation flickers in bursts, triggered by tides and internal feedback from supernovae. A few are already being pulled apart, shedding stars into long, cold streams that wrap the sky like pale ribbons. Those streams are not just debris, they are orbit tracers, sketching the Milky Way's gravitational field in faint, coherent arcs. The Milky Way, Andromeda pair, is a binary system in slow motion, separated by roughly 2.5 million light-years of dark space. Their mutual gravity defines a barycenter that sits between them, closer to Andromeda because it is slightly more massive. Each galaxy moves around that shared center while also responding to the group's overall pull, and the motion is measured through careful astrometry and Doppler shifts. Even their extended dark matter halos, far larger than their visible disks, overlap in influence, shaping satellite orbits long before any luminous collision begins. In simulations, those halos are the true sizes of the galaxies, and the stars are only the bright inner frosting. The local group is not a static list of members, and it is not a tidy classroom diagram. It is a gravitational negotiation between two large halos and many smaller ones, with orbits that can be tilted, precessed, and heated over time. Satellites trace those halos, and their orbits reveal mass that does not shine. When a dwarf galaxy moves too fast to be held by visible stars alone, the missing binding mass points to dark matter, the dominant component of the halos. The same logic, velocity implying mass, echoes from galaxy rotation curves all the way up to cluster dynamics. Those orbits are also fossils of assembly, preserved in the geometry of motion rather than in a simple picture. Some satellites arrived as pairs or small associations, falling in along preferred directions that reflect the larger-scale filaments feeding the group. Others were captured long ago and have been stirred by repeated passages through the Milky Way's outer regions, where tides stretch them and shocks strip their gas. The result is a living system, where the past is written in phase space, positions and velocities, rather than in a static sky map. When we measure proper motions of nearby dwarfs, we're effectively reading a time-lapse of the local group's growth. The long-term fate is not mystery, only timescale, and the timescale is measured in billions of years rather than in human epochs. Andromeda is approaching at roughly 100 kilometers per second in radial velocity, a closing speed derived from its blue shift. Proper motion refines the trajectory, but the broad outcome remains a merger in several billion years, as dynamical friction bleeds orbital energy into the surrounding halos. When it happens, it will be less like two solid objects colliding, and more like two diffuse gravitational ecosystems interpenetrating, with stars mostly passing by one another. Gas clouds, however, will collide and compress, and that compression can ignite new waves of star formation before the system relaxes. A future collision is also a reminder of the present, because the local group is already interacting internally. Even now, the Milky Way's halo is interacting with its neighbours through tides, streams and shared infell, and the evidence is written across the sky. The Magellanic Clouds tug at our outer disk and stir our halo gas, leaving wakes and distortions in the circumgalactic medium. The Sagittarius dwarf, in the process of being shredded, has likely helped excite ripples in the Milky Way's stellar disk, like rings spreading across a pond after a distant impact. In Gaia's star maps, those ripples appear as subtle patterns in velocity and density, a reminder that our disk is not perfectly settled. The local group is a bound structure, but it is also moving through an even larger landscape, and that landscape is not optional. Our galaxies are not simply orbiting each other in isolation, because they are embedded in a broader pattern of density variations that extends far beyond the reach of any single halo. In a universe shaped by gravity, isolation is the exception, not the rule, and local is always nested inside something larger. So the paradox resolves into a better question. If the solar system is carried by galactic gravity, what carries the galaxy itself? To answer, we give our cosmic address in layers, and each layer comes with a different kind of evidence. The local group sits near the outskirts of the Virgo cluster region, where the galaxy density begins to rise. The Virgo cluster is a dense node of galaxies, a true cluster with hot intracluster gas and deep gravitational potential. In X-ray light, that gas glows as a vast, thin atmosphere heated to tens of millions of degrees by the cluster's gravity, and stirred by mergers that drive shocks through the plasma. The brightness is not starlight at all. It is Bremsstrahlung radiation from electrons slowed in the electric fields of ions. Visually, Virgo is not a single object, but a crowded volume where galaxies swarm like insects around a lantern. Elliptical galaxies dominate the core, their stars old and reddish, while spirals are more common in the outskirts where gas survives longer. The cluster environment is harsh, and it is harsh in specific physical ways. As galaxies plunge through the hot intracluster medium, ram pressure can strip their gas, quenching star formation and transforming their appearance over time. Tidal encounters also matter, because repeated fast flybys can thicken disks and scramble orbits, gradually converting graceful spirals into smoother, gas-poor systems. Historically, astronomers used Virgo supercluster as a broad name for the surrounding concentration. It was a convenient label for a local overdensity centered roughly on Virgo, and it helped organize a sky that was otherwise just a scatter of redshifts. As mapping improved, the label became less precise than the data demanded, because the structures were not isolated blobs. The word supercluster suggested a discrete object with a clean boundary, but the universe rarely offers clean edges at these scales. Instead, it offers gradients, densities that fade into filaments, and filaments that thread into other nodes. There is also a history of method behind the naming, and that method shaped what people thought they were seeing. Early redshift surveys, built galaxy by galaxy, revealed that the nearby universe is lumpy, and that the lumps had preferred shapes. By the late 20th century, projects like CFA showed that galaxies trace filaments and walls, with voids in between, and the maps looked almost biological. Those surveys made it harder to pretend that Virgo supercluster was a single, self-contained island, because the data revealed bridges and corridors of galaxies leading away from Virgo in multiple directions. A newer name, Laniakea, reframes the idea as a basin of attraction. It is defined not by a boundary drawn on a map, but by the directions galaxies flow, as inferred from peculiar velocities. In this view, home is the region whose galaxies share a common gravitational drainage, moving coherently toward the same general basin. The name itself, meaning immense heaven, is poetic, but the definition is technical, grounded in velocity fields rather than in simple density counts. It is also a shift in philosophy, because it treats motion as primary evidence and light as an incomplete tracer. Laniakea includes the local group and extends across hundreds of millions of light years, spanning a volume so large that no single image can contain it. Its edge is not a wall of matter, and it is not even a sharp transition in galaxy counts. It is a watershed line where galaxy motions diverge toward different attractors, like rain deciding which valley it will enter. Cross that invisible ridge, and the same expansion of space carries galaxies outward. Yet their peculiar motions tilt toward a different gravitational low. The boundary is dynamic, defined by vectors rather than by a drawn contour. This is where above and below become physical again, but not vertical. They become downhill and uphill in gravitational potential, and the potential is inferred rather than directly seen. The universe becomes a terrain of valleys and ridges, and galaxies become tracers sliding along the slope. The landscape is not made of rock, but of curvature, space-time responding to mass and energy. In plain language, matter tells space how to bend, and the bending tells matter how to move. On screen, the map becomes topography, but the topography is built from data points and uncertainty cones. Flow lines stream like rainwater on a mountainside, bending around high ground and converging into basins that deepen where mass accumulates. The metaphor is imperfect, yet it is close enough to guide intuition, because it captures directionality and convergence. Gravity does not pull from a single point here. It emerges from the combined influence of structures spread across enormous distances, and the sum can be stronger than any individual contributor. The terrain is not smooth, and it never was, because the early universe was not perfectly uniform. On the largest scales, matter forms a cosmic web of filaments, nodes, and voids, a pattern that appears again and again in surveys. Filaments are elongated bridges of mass and galaxies, often hosting groups and clusters along their lengths. Nodes are clusters where filaments intersect and matter piles up. heating gas and deepening potentials. Voids are the wide, dim spaces between, where galaxies are sparse and the density is low, and where the sky feels suddenly empty. Voids are not empty, but they are underdense compared with the mean, and their physics is distinctive. They expand faster than average because there is less gravity to slow them, so their local Hubble flow is slightly higher. Their growth helps push matter into the surrounding filaments, sharpening the web's contrast and thickening the walls. Over cosmic time, that contrast increases, turning small early differences into the dramatic structures we map today. In simulations, voids become the negative sculpting tool, carving out the spaces that make filaments stand out. The cosmic web is not an artistic metaphor, and it is not a pattern we imposed after the fact. It is the generic outcome of gravity acting on tiny early fluctuations, amplified over billions of years. Simulations starting from CMB-measured seeds grow filaments and clusters with striking realism, and they do so with no special tuning of shapes. When the initial conditions match the observed spectrum of early density variations, the resulting web resembles what surveys actually see, down to the statistics of clustering. The agreement is one of cosmology's quiet triumphs, because it links the oldest light to the newest structures. Those early fluctuations were small, parts in 100,000 in the CMB temperature field, yet they were enough. Gravity amplifies them slowly at first, then more efficiently as matter dominates over radiation, allowing perturbations to grow. Regions slightly denser than average decelerate their local expansion, turn around and begin to collapse, gathering more matter as they deepen. Regions slightly emptier do the opposite, becoming the voids that define the web's negative space. The universe is not choosing patterns, it is simply letting small differences compound. In those simulations, dark matter does the first sculpting, because it is collisionless and responds cleanly to gravity. It collapses into a network of halos and filaments because it interacts mostly through gravity, forming the scaffolding before gas can cool. Baryons fall into those potential wells, shock, cool, and light up as galaxies, and the process leaves observable signatures. The physics is layered, dark matter sets the stage, gas dynamics writes the script, and star formation provides the visible glow. Feedback from stars and black holes then edits the script, blowing gas out and regulating how bright the galaxies become. This is why luminous matter traces invisible structure, but never perfectly. Galaxies are not randomly sprinkled through space. They mark where dark matter has already built the scaffolding, yet the brightness depends on how efficiently gas turned into stars. Even when we see only a few bright galaxies, the filament they trace can contain a much larger mass of dark matter, plus diffuse gas that is difficult to detect directly. In some wavelengths, that gas appears as absorption lines in quasar spectra, a faint fingerprint of the web's hidden baryons. The web also explains why our earlier detector volume problem never ends, because the space between source and observer is active. A messenger from above crosses filaments, voids, and halos before reaching us, and each region can imprint its own signature. Some signals are source-dominated, but many are path-shaped by intervening structure, sometimes subtly and sometimes dramatically. The universe is not a transparent vacuum at every wavelength, and it is not magnetically quiet. Even the emptiest-looking regions can contain tenuous plasma and weak fields that matter for long journeys. A photon's journey can be altered by absorption and scattering, while a charged particle's path can be bent by magnetic fields. Even gravitational lensing, mass-warping spacetime, can magnify or distort distant sources, and it can do so without adding any light of its own. The same structures that guide galaxy flows also act as lenses and filters, imprinting themselves on what arrives at our instruments. Sometimes the imprint is a distortion in shape, and sometimes it is a bias in where we think the source must be. To turn this web into a map, we need distances and velocities, and we need them independently. Redshift gives a recession velocity dominated by cosmic expansion, but it blends expansion with local motion along the line of sight. Distance indicators give an independent measure of how far away a galaxy actually is, and those indicators are hard-won. When both are available, the difference between expected and observed recession becomes a diagnostic of local gravity. In effect, we compare where a galaxy is to how fast it seems to be leaving, then infer the tug that must be acting. When we compare the two, we separate Hubble flow from peculiar velocity. Peculiar velocity is the deviation from pure expansion, caused by local gravity and the uneven distribution of mass. It is the signature of mass pulling matter off the idealized Hubble line, creating coherent streams and convergences. In practice, it is also a reminder that the universe is not perfectly uniform, even though it is statistically homogeneous on very large scales. The deviations are not noise, they are the point. Distance is the hard part, and astronomy built a ladder to reach it, rung by rung, with calibration at each step. The Tully-Fisher relation links a spiral galaxy's rotation speed to its luminosity, turning a measured line width into an estimated absolute brightness. Type Ia supernovae act as standardized candles after calibration, extending the reach much farther than galaxy scaling relations alone. Each method carries scatter and systematic uncertainties, so the ladder works best when multiple rungs overlap and cross-check one another. The cross-checking is crucial, because flow maps can be biased by even small distance errors. The Tully-Fisher relation is rooted in dynamics, and dynamics is ultimately about mass. Faster rotation implies a deeper gravitational potential, which correlates with total mass and, statistically, with luminosity, especially in the near-infrared where dust effects are smaller. Yet dust, inclination, and star formation history complicate the measurement, and even the choice of photometric band matters. Astronomers correct for these effects carefully, because a small bias in distance becomes a large bias in inferred flow. A few % error in distance can masquerade as a significant peculiar velocity. Type A supernovae, by contrast, are brief but extraordinarily bright, and their physics is remarkably consistent. Their peak luminosities are not identical, yet their light curve shapes correlate with intrinsic brightness, allowing standardization after careful fitting. With calibration, they become reliable distance markers across hundreds of millions, even billions of light years, and they anchor the far end of the ladder. In a flow map, they are like flares thrown into the dark, momentarily revealing the structure of the surrounding space. Each event is a single point, but together they build a statistical skeleton. With these tools, surveys measure galaxy distances and infer peculiar motions, and the logic is simple even when the data are not. A galaxy that is closer than its redshift implies is moving away slower than Hubble flow predicts, as if it is being held back by gravity. A galaxy that is farther than its redshift implies is moving toward us relative to the expansion, as if it is falling into a nearby overdensity. The sign matters, but so does the coherence across the sky, because coherent patterns reveal large-scale gravitational influence. Random errors average out, but coherent streams remain. Peculiar velocity maps are not just kinematics, because kinematics is a shadow of mass. They are indirect maps of mass, including mass that emits no light and may never emit it. Where flows converge, gravity is stronger than visible matter alone often suggests, implying hidden mass in halos, filaments, or cluster outskirts. Where flows diverge, we infer underdensities, voids whose relative emptiness allows faster expansion. In this way, motion becomes a probe of the invisible, and the invisible becomes a measurable hypothesis. This is the deeper meaning of below in this chapter. Below is the direction of net acceleration in the local cosmic flow, defined by the gradient of gravitational potential. It is the direction the Milky Way is being pulled, even when the sky looks symmetric and calm. The pull is not a rope tied to a single galaxy. It is the sum of countless contributions from structures across a wide region, each too weak alone but powerful together. The sum is what we feel as a drift in the CMB frame. We can measure our motion in a way that does not depend on local structures at all, and that is what makes it so powerful. The cosmic microwave background provides a universal rest frame, defined by the average motion of matter at the time of last scattering. It is relic radiation from the hot early universe, now cooled to a few Kelvin by cosmic expansion. It fills all of space, arriving at Earth from every direction with remarkable uniformity, like a faint thermal glow behind everything else. When we look at it, we are looking back to a time before galaxies existed. If we were at rest with respect to that radiation, the CMB would look nearly the same in every direction, aside from tiny primordial anisotropies. Instead, it shows a dipole anisotropy, a simple two-lobed pattern laid across the sky. One side of the sky is slightly hotter, the opposite side slightly cooler. The effect is subtle enough that it must be measured with careful instruments, yet it is clear enough to stand out above the CMB's finer-grained fluctuations. It is the cleanest large-scale feature in the microwave sky. The dipole is a Doppler effect from motion, and it is almost embarrassingly direct. We move toward the hotter direction, boosting the photon's energy and making the spectrum appear slightly warmer. We move away from the cooler direction, reducing their energy and making the spectrum appear slightly cooler. The physics is familiar from sound, but here it is written in microwaves, ancient light stretched by expansion, since the universe was only about 380,000 years old. The dipole is not about early density seeds, it is about us now. The temperature difference is tiny, but it encodes a large velocity, because even a small fractional shift in temperature corresponds to a significant speed. The inferred speed is about 370 kilometers per second relative to the CMB rest frame, a number that becomes a cornerstone for local cosmography. The entire universe becomes a reference for direction, even when space has no absolute up. It is as if the cosmos itself provides a compass, not by magnetism, but by thermodynamics and motion. The arrow is written into the sky's background glow. On screen, the dipole appears as a smooth gradient across an all-sky map. One hemisphere blushes slightly warmer, the other slightly cooler, like a barely perceptible tide of colour. The simplicity is striking, because it looks almost too clean to be real. Beneath the detailed mottling of primordial fluctuations lies a global arrow pointing to our motion. It is the kind of measurement that feels like a revelation because it is both subtle and decisive. That dipole direction is not the same as our orbit around the galactic centre, and that mismatch is the clue. It is the vector sum of many motions stacked together, each with its own origin and timescale. Earth around the Sun around the Milky Way within the local group, and the local group within larger flows. Each component is measurable, and each must be accounted for before the deeper drift becomes visible. Only after subtraction does the large-scale current emerge. When we subtract known components, a residual remains that points outward into intergalactic space. That residual is the clue that our neighbourhood is falling towards something massive, and that the pull is not local. It is the clue that the cosmic web is not only structure, but motion, and motion that remains coherent across vast distances. The web is not frozen in place, it is a dynamic pattern, still responding to gravity after billions of years, even as expansion continues to stretch the stage. The story of that motion has a name that sounds like myth, yet it emerged from hard data and persistent discrepancy. The Great Attractor is a region of mass over density inferred from galaxy-peculiar velocities, not from a single dramatic image. It is not a single object, but a gravitational influence spread across a broad volume, containing clusters, groups, and filamentary mass. The name can mislead, because it suggests a solitary monster, when the reality is a complex region embedded in the web. The Attractor is a basin in the flow field, not a point. The Great Attractor was inferred because galaxies in our region show coherent streaming, and the streaming is directional. Their redshifts and distances do not match a simple expansion centered on us. They reveal a drift toward a common direction, like water bending toward a drain, and the drain is defined by convergence. The pattern appears in many independent datasets, which is why it survived skepticism and refinement. When different distance methods agree on the same drift, the universe is telling you something consistent. Historically, this was a moment when the local universe stopped being nearby in a comforting way. Astronomers realized that even tens of thousands of galaxies could share a bulk motion relative to the CMB frame, implying a gravitational influence on enormous scales. The implication was unsettling and elegant at once. Large-scale structure was not merely a backdrop, it was actively shaping trajectories across hundreds of millions of light-years. The sky's apparent stillness was hiding a slow, coordinated migration. The inference was complicated by a practical obstacle, and the obstacle was literally in the way. The suspected direction lies near the plane of the Milky Way, where dust and dense star fields obscure external galaxies. This is the zone of avoidance, where optical surveys struggle and where catalogues historically thinned. In visible light, the sky there is saturated with foreground stars, and the dust lanes cut dark seams that hide what lies beyond. The missing data were not cosmic emptiness, but observational blindness. The zone of avoidance is not a true absence of galaxies. It is an observational blind spot created by our own disk, with extinction, confusion, and crowding all working together. The Milky Way becomes foreground contamination in the most literal sense, turning our home into a veil. The irony is sharp. Our home galaxy, which we study in exquisite detail, also blocks our view of the larger structures that help carry it along. To map the flow, we had to learn how to look around ourselves. To see through it, astronomers changed wavelengths, turning the electromagnetic spectrum into a set of alternative windows. Infrared surveys penetrate dust far better than visible light, because longer wavelengths scatter less. Radio surveys, especially the 21 centimetre line of neutral hydrogen, can detect gas-rich galaxies even behind heavy extinction. These methods do not erase the foreground, but they reduce its power to hide the background. They also change what kinds of galaxies we find, emphasizing dusty and gas-rich systems. Infrared light slips through dust grains that would scatter or absorb shorter wavelengths. In infrared maps, the Milky Way's obscuring lanes become translucent, and external galaxies reappear as faint smudges behind the stellar crowd, often clustered where the Webb predicts they should be. Radio observations go further in a different way. The 21 centimetre line, produced by a hyperfine transition in neutral hydrogen, can be measured with high spectral precision, yielding redshifts even when optical images are compromised. With enough sensitivity, the line reveals rotation widths too, feeding directly into Tully, Fisher distances. Those surveys filled in missing pieces of the map, and the map changed character as the holes shrank. They revealed galaxies and clusters hidden behind the Milky Way's glare, turning a suspected overdensity into a structured region. The Great Attractor became less a rumour and more a measurable region in a larger flow network. As the blind spot shrank, the flow field became less ambiguous, and the inferred mass distribution became more consistent with the observed structures. The attractor was still complex, but it was no longer invisible. Yet the Great Attractor is not the end of the pull, and that is where the narrative deepens. Farther away lies the Shapley concentration, an even larger overdensity of galaxy clusters. It sits hundreds of millions of light-years away and appears to contribute significantly to our bulk flow, adding a longer lever arm to the gravitational landscape. In terms of raw mass, it is among the most substantial concentrations in the nearby universe. Its influence is not about a single cluster, but about a packed region where many clusters live close together. In modern reconstructions, the flow lines do not simply terminate at the Great Attractor. They continue toward Shapley, suggesting a chain of attractions across scales like nested basins in a larger watershed. Our motion is not toward one monster, but along a gradient built by multiple mass concentrations, each shaping the slope. Gravity at these distances behaves less like a point force and more like a landscape shaped by many hills and basins. The direction we infer is therefore a summary of a complicated distribution. On screen, the flow visualization becomes more dramatic, and the camera seems to glide along invisible currents. Streamlines that began near our local group arc past Virgo's influence, then bend toward the hidden mass behind the Milky Way. Beyond that, the lines continue, tightening again as they approach the Shapley region, where the basin deepens. The sense is not of a single destination, but of a connected network of pulls that overlap and reinforce. The universe looks less like a map of places and more like a map of tendencies. This is where the chapter becomes the climax, because the scale ladder finally links back to our smallest motions. The solar system's motion is not only a local drift through gas and magnetic fields, it is part of a gravitational relay, passed from planet to star, from star to galaxy, from galaxy to supercluster. The same physics that keeps the Moon in orbit also shapes the trajectories of galaxy groups, just with different masses and vastly longer clocks. The equations do not change, but the intuition must stretch. The existential tension is not about danger, but about agency, and the feeling is quietly profound. We do not choose the direction of this current, and we do not feel it in our bodies. We infer it from tiny spectral shifts and faint standard candles, then realize it reaches across a significant fraction of the observable local universe. The conclusion arrives gently, but it lands with weight. Our rest is only ever relative. Even the calmest sky hides a measured drift. The cosmic web is the architecture above us. The basin of attraction is the slope below us. Between them, the Milky Way is a luminous raft carried by invisible mass, and the raft is not centered in the river. Its stars trace a bright spiral pattern, yet most of its gravitating content is dark, and most of its motion is dictated by structures far beyond its disk. The galaxy's beauty is real, but its control over its own trajectory is limited. This also resolves a question planted earlier about high-latitude messengers, because direction alone never tells the full story. When a particle or photon arrives from above, we must ask what shaped its path and what it crossed on the way. The halo, the local group medium, and the cosmic web all add foregrounds, deflections, and absorption, and those effects can mimic or mask sources. The sky is not a simple sphere of sources. It is a layered medium with history, and the layers are part of the signal. Some gamma rays are truly extragalactic, but many are filtered by intervening radiation fields, losing energy through interactions over long distances. Ultra-high energy cosmic rays are bent by magnetic fields in galaxies and filaments, turning a straight-line clue into a scrambled arrival direction. Neutrinos pass more cleanly, yet even they are counted against backgrounds that must be modelled, and their sources are rare. The practical challenge is also philosophical. How much of what we see belongs to the source, and how much belongs to the space between? When we interpret the sky, we're also interpreting the journey. The lesson is methodological as much as cosmic. We do not map the universe by light alone, because dust hides and distance deceives, and brightness is not the same as mass. We map it by motion, because gravity leaves fewer places to hide, and coherent flows are difficult to counterfeit. Motion is not immune to uncertainty, but it is harder to fake. A coherent flow pattern demands a coherent mass distribution, whether or not that mass shines. In that sense, velocity fields are a kind of honesty test for cosmological maps. Peculiar velocities become a kind of gravitational tomography, turning line-of-sight measurements into three-dimensional inference. They reveal where mass must be, even if it is dark, diffuse, or buried behind the Milky Way. They also reveal where our models are incomplete, because flows can disagree with visible matter distributions. When that happens, the disagreement is not merely an error bar. It is a clue that something unseen is shaping the field. The web is not only what we see, but what we must infer. In this language, above and below are not two hemispheres. They are two sides of a potential gradient, defined by acceleration rather than by geometry. Above is the direction of lesser pull, toward voids and expanding regions where matter thins out. Below is the direction of greater pull, toward filaments, clusters, and deepening wells where matter gathers. The words become relational rather than absolute, and the relation is measurable. The sky becomes a field of vectors, not just a dome of lights. The Milky Way's own motion is therefore a local measurement of the cosmic web, taken from inside the web itself. The CMB dipole gives the broad vector, anchored to the universe's oldest light. Peculiar velocity surveys provide the detailed streamlines that connect us to nearby basins, revealing how the broad vector is built from local pulls. Together, they turn the abstract idea of large-scale structure into a measurable set of directions, with uncertainties that can be quantified and improved. Each new survey tightens the picture, and each correction sharpens the flow. We can now state our address as a motion, not a coordinate, and that shift matters. We are in the Milky Way, within the local group, within the Laniakea Basin, moving with a bulk flow toward the Great Attractor region, and onward toward Shapley. It is a sentence that contains both location and trajectory, as if where and going have merged into a single description. The address is not a pin on a map. It is a vector through a landscape. That address is unsettling because it is dynamic, and dynamics implies that the present is not a final arrangement. It says we're not merely located within structure, we are being carried by it, and the carrying is measurable in the sky's oldest light. The CMB dipole is not a story we tell ourselves. It is a gradient written into the microwave sky, indifferent to our interpretations. The universe does not need our metaphors to keep moving. So the paradox resolves into a better question. If we have mapped matter and motion, what else fills every direction regardless of structure? Because even if galaxies were removed, the universe would not be empty, and that is the next reveal. Backgrounds remain that do not belong to any one galaxy, and they are part of the universe's inventory. Relic light fills space, relic neutrinos stream through it, and vacuum energy shapes expansion itself. These components are not arranged like the web, they are everywhere, and their uniformity is part of what makes them so strange. They are the quiet stage on which the web performs. The CMB is the most visible of these backgrounds, a near-perfect black-body spectrum that tells us the early universe was hot, dense, and close to thermal equilibrium. Its uniformity is a triumph of cosmology, because it implies that distant regions once shared a common thermal history. yet its tiny anisotropies are equally important, because they are the seeds from which the web grew. They are the reason the web exists at all, and they let us connect the present structure to initial conditions. Neutrinos add another layer, almost ghostly in their elusiveness, and their influence is subtle but real. They rarely interact with matter, so they stream through galaxies, planets, and bodies without notice, carrying energy and momentum almost untouched. In the early universe, they were abundant and energetic, helping shape the growth of structure by free streaming across small scales and smoothing out some clumping. Even now, their presence is inferred through cosmological constraints, a reminder that invisible does not mean absent. We live in a sea of particles that almost never say hello, and then there is vacuum energy, the component that appears to drive accelerated expansion, changing the long-term balance between pull and drift. It does not clump into filaments, it does not form halos, yet it changes the long-term fate of flows, because it alters how expansion competes with gravity over time. The web evolves within that larger context, growing in some ways while being stretched apart in others. Gravity builds structure, but accelerated expansion limits how far that building can continue. This is the handoff to the final chapter. We have followed the pull lines outward until below becomes a cosmic basin, and the basin becomes part of a larger watershed. Now we turn to what is truly everywhere, including above and below the solar system, even in the deepest voids. The universe is not only a map of structures, it is also a set of backgrounds, quiet, pervasive, and fundamental, waiting to be understood. We return to the question that started the journey, because the sky still feels directional and strangely weighted. Above us is a rain of invisible bullets from distant explosions, arriving at near-light speed with indifferent precision. Below us is a silent gravitational current that never stops pulling, an acceleration we feel as down, even when the planet is not in frame. The first correction remains the most important, and it is also the most counterintuitive. Space has no absolute up or down, and there is no universal floor beneath the stars. Yet above and below become meaningful when we choose a frame, and the galaxy quietly provides one. Relative to the galactic plane, north and south are not empty hemispheres painted onto a dome. They are columns through layered media, through magnetic structure, and through gravitational potential that changes with height. When we say vertical, we mean through those layers, through an atmosphere of gas and fields, not away from reality. In visual terms, imagine a thin, luminous disk crossing the sky, with a faint haze rising from it like breath. The disk is crowded with dust lanes and star clouds, while the poles look cleaner and deeper. That contrast is not just aesthetic, it is physics written as brightness, opacity, and signal to noise. So the paradox resolves into a better question: what fills every direction even when structure seems absent? Start with the backgrounds that do not belong to any one place, because they were born before galaxies existed. The cosmic microwave background is relic light from the hot, early universe, released when electrons and nuclei first combined. It fills all space nearly uniformly, a near-perfect blackbody cooled by expansion to about 2.7 Kelvin. On an all-sky map, the CMB looks like mottled static, but the mottling is a fossil. Those temperature variations are only tens of microkelvin, yet they encode the density ripples that later grew into clusters and voids. It is the oldest photograph we possess, and it is also a set of initial conditions. The CMB answers above and below with indifference because it arrives from every direction with almost equal intensity. Yet it also reveals direction through anisotropy, and that is where the uniformity becomes useful. Tiny primordial fluctuations seed the cosmic web, and a larger dipole encodes our motion through the microwave rest frame. That dipole is not a decoration on a map, and it is not an artifact of our instruments. It is a velocity measurement written into the microwave sky, a subtle gradient that repeats no matter how we observe. We move through the CMB rest frame, and the sky becomes slightly hotter ahead and cooler behind. Historically, this was a turning point, because it made motion relative to the universe a measurable statement. The dipole's amplitude corresponds to a few hundred kilometers per second, which is fast by human standards and modest by cosmic ones. It reminds us that even a seemingly fixed sky is a reference frame we can drift through. The second background is harder to even name, because it has never been directly imaged in the way the CMB has. The cosmic neutrino background should be everywhere, a relic C from the first seconds when the universe was denser than any star. It is predicted by the same thermal physics that predicts the CMB, yet it barely interacts with matter. Neutrinos decoupled earlier than photons, so in principle they carry information from a younger universe. Today they should be extremely cold and numerous, passing through Earth and our bodies without leaving a trace. Their ghostly nature is not poetic license. It is a consequence of weak interactions and tiny cross-sections. Neutrinos already shape the universe in indirect ways, and the evidence is written in patterns rather than tracks. Their masses and free streaming suppress small-scale clustering, leaving fingerprints in large-scale structure and in the CMB power spectrum. The C is almost undetectable locally, but it is not optional cosmologically. There is a quiet lesson here about everywhere backgrounds because they can be real without being visible. A background can be inferred from what it prevents, from what it smooths, and from how it changes growth over billions of years. In that sense, the neutrino sea is like a wind felt through the bending of trees, not through the sight of air. A third background is newer to our imagination, and it changes what listening can mean. A gravitational wave background should fill space-time, built from countless mergers and possibly early universe processes that stretched and rang the fabric itself. It is not light and not particles, yet it carries energy and information as distortion. Unlike photons, gravitational waves pass through dust and plasma almost unimpeded, because they couple to mass energy in a different way. They do not scatter off electrons, and they do not care about magnetic fields, yet even they can show anisotropy, because sources cluster in galaxies and along filaments. In practice, everywhere can still carry a faint direction, and the sky can still have a grain. A background assembled from many events inherits the universe's uneven distribution of matter. Even a hum can have a chorus line, louder where the cosmos is crowded. These backgrounds do not care about the galactic plane, but our measurements do, and that is the next reveal. Our motion, our shielding, and our foregrounds modulate what we infer, adding biases that mimic structure. Above and below become partly about the universe, and partly about the observer who is embedded in local weather. Now we rebuild the vertical atlas from the inside out, because the local layers decide what reaches us and what is filtered away. Shell 1 is the heliosphere, inflated by the solar wind and threaded by the interplanetary magnetic field. It is a moving, breathing boundary, not a static bubble drawn with a compass. Picture the sun as a lighthouse that also exhales, sending a supersonic plasma flow into interstellar space. That wind carries magnetic field lines outward, twisting them into a spiral as the sun rotates. Where the wind finally slows against the interstellar medium, boundaries form: termination shock, heliosheath, and heliopause, each one dynamic. The heliosphere filters charged particles by rigidity and by magnetic geometry, and that filtering is energy dependent. Lower energy cosmic rays are deflected more easily, while higher energy particles punch through with less bending. Over the solar cycle it expands and contracts, changing the cosmic ray spectrum that reaches Earth. Voyager showed the boundary is porous and turbulent, with draped fields and reconnection that resembles space-scale weather fronts. The crossing was not a clean pop through a membrane, but a sequence of changing plasma conditions. Even the idea of inside and outside becomes fuzzy when the boundary ripples. The heliosphere also sets a baseline for space weather beyond Earth's atmosphere, and it sets it for decades at a time. When it's stronger, fewer low-energy galactic cosmic rays penetrate inward, and the inner system is quieter. When it is weaker, the inner system becomes more exposed, and atmospheric chemistry responds. Shell 2 is the local bubble, and its nearby clouds, a carved cavity within the galactic disk that we inhabit without seeing. The sun sits in warm, partially ionized local fluff embedded in hotter, lower-density plasma. Dust and gas are not evenly mixed, and the bubble walls matter like the walls of a cavern. Visually, the local bubble is a hollow in the interstellar fog, bounded by brighter ridges where gas piles up. Those ridges show up in maps of dust extinction and in soft X-ray emission, though interpretation is delicate. The bubble is not a perfect sphere, and its edges are scalloped by past shocks. The bubble's history is written in supernova archaeology, where we read isotopes and kinematics like clues at a scene. Multiple explosions from nearby stellar groups likely excavated the cavity, and iron 60 on Earth supports recent nearby events. The bubble is not just a place, it is a timeline of shocks, heating, and cooling. That history matters because supernovae do more than clear space. They seed it with turbulence and magnetic structure. Shock waves compress gas, amplify fields, and accelerate particles through repeated crossings, a process known as diffusive shock acceleration. The bubble's interior is therefore not empty, but conditioned by violence. The local bubble is also not closed, and this is where above begins to open into the halo. Chimneys and openings vent toward higher latitudes, linking disk gas to pathways that rise away from the plane. Those vertical corridors change where hot plasma flows, where cosmic rays diffuse, and where soft X-ray emission is produced. Shell 3 is the Milky Way's disk and halo, the layered atmosphere that makes above and below physically different in a measurable way. Near the mid-plane, cold gas and dust dominate and star formation is active, bright in infrared and crowded in catalogues. Higher up, warm ionized layers give way to hot halo plasma and sparse stars. The disk is thin compared to its diameter, so a small change in latitude changes the column of material dramatically. Looking along the plane, starlight is reddened and blocked by dust, and radio emission is cluttered by overlapping sources. Looking toward the poles, the path is shorter through the disk, and the sky becomes a cleaner window. Magnetic fields thread every phase, and they turn straight-line intuition into a trap that observers must constantly correct. Charged cosmic rays are bent and scattered, so arrival directions rarely point back to sources with any honesty. The field geometry also creates highways and bottles, shaping confinement, diffusion, and eventual escape into the halo. Those fields are not uniform bars, but tangled structures with coherent components and turbulent cascades. Faraday rotation and synchrotron polarization reveal spirals, reversals, and patches of ordered field aligned with the disk. When we say magnetic scaffolds, we mean a three-dimensional architecture that guides charged messengers. Gamma rays and neutrinos cut through that confusion, but they still inherit foregrounds that must be modelled rather than wished away. Gamma rays trace cosmic ray collisions with gas and radiation fields, so the path and the targets matter. Neutrinos pass more cleanly, yet their statistics are sparse and backgrounds are stubborn. In gamma rays, the Milky Way glows because cosmic rays constantly strike interstellar gas, producing pions that decay into high-energy photons. In addition, electrons scatter starlight and infrared light through inverse Compton processes, adding a diffuse component. Each mechanism has its own spatial signature, so above and below become diagnostic. This is where the Fermi bubbles become a vertical landmark and a kind of exclamation point in the halo. Two giant lobes rise above and below the galactic center, with hard spectra and sharp edges, as if carved with a blade. They imply major energy injection into the halo, from past black hole activity or nuclear star formation. On a visualization, the bubbles look like twin lanterns extending tens of thousands of light years, faint but unmistakable once you know how to subtract the foreground. Their edges suggest a boundary between shocked and unshocked plasma, and their uniform brightness hints at transport and mixing. They are a reminder that the galaxy has moods and episodes. The bubbles also resolve a lingering ambiguity from earlier chapters, because they teach caution about latitude. High latitude emission is not automatically extragalactic, and clean does not always mean distant. Sometimes the Milky Way is speaking through its halo, and we must separate local structure from faraway populations. Shell 4 is the cosmic web, inferred from galaxy surveys, peculiar velocities, and the CMB frame that gives us a universal yardstick. It is not a shell of matter around us, but a network of filaments and voids that defines large-scale flows. It gives below a new meaning as downhill in gravitational potential, even when the sky looks symmetric. The CMB dipole provides the broad vector of our motion, and velocity surveys provide the streamlines traced by galaxies. Together they show our galaxy is carried toward a basin of attraction, shaped by multiple overdensities rather than a single monster. Above and below become aligned with flow, not with a sky dome. There is an observational humility built into this because the flow field is reconstructed, not photographed. Distances have uncertainties, velocities have noise, and the map improves as surveys deepen. Still, the pattern is persistent. Matter gathers, gravity pulls, and our local group rides the gradient. Now we connect the shells because the story is not 4 separate maps pinned to different walls. The heliosphere rides through the local bubble, and the bubble sits inside the disk like a cavity in layered rock. The disk is embedded in the halo, and the halo moves through the cosmic web that sets the long-range tide. Motion through structure changes exposure, and it changes interpretation in ways that are easy to underestimate. A moving observer sees anisotropies even in nearly uniform backgrounds, and sees different columns through dust and gas. The same sky can look different in different epochs of our orbit, even when the universe itself is unchanged. Time dependence is the missing axis in the vertical picture, and it turns geometry into history. The Sun oscillates through the galactic plane on tens of millions of years timescales, sampling denser and thinner layers as it bobs. It also orbits the galaxy in a few 100 million years, crossing spiral structure and changing neighbours. Imagine a slow wave motion, like a ship rising and falling on an ocean swell, except the ocean is gas density and magnetic pressure. Each passage through the mid-plane changes the average column of material above and below, and it changes the local rate of encounters. Even the cosmic ray environment is not fixed, because sources are clustered and transient. Plane crossings do not guarantee catastrophe, but they change probabilities in a way that matters to long-term habitability. Near the mid-plane, gas density and cloud encounters are higher, and massive stars are more common. That raises the chance of nearby supernova, changes cosmic ray production, and modulates the galactic tide that tugs on distant orbits. The changing tide matters because the outer solar system is sensitive to gentle, persistent forces rather than dramatic ones. The Oort cloud is weakly bound and responds to small perturbations accumulated over long times. Disk and halo gravity plus passing stars and clouds can inject comets inward over millions of years. Time dependence also matters for shielding, because the heliosphere is a pressure balance, not a fortress. If the Sun moves into a denser interstellar cloud, external pressure can compress the heliosphere and reduce its protective volume. That can increase cosmic ray flux at Earth, altering atmospheric ionization and potentially climate-linked chemistry. This is the unified answer to the hook, and it is more physical than it first appears. Space feels like an unseen ocean because it is filled with fields and particles that we mostly do not see directly. We detect them through effects, through anisotropies, and through how they modulate one another across scales. Yet the inventory is not complete, and the unknowns are not cosmetic details at the edge of a finished map. We still do not know how clumpy the dark matter halo is in our neighbourhood, or how much substructure survives. Streams and subhalos could alter the local dark matter wind, complicating direct detection expectations and annual modulation searches. We still do not have the full baryon budget of the circumgalactic medium, the extended reservoir that surrounds the Milky Way. Hot, diffuse gas may hide much of the missing ordinary matter, but its density, extent, and multi-phase structure remain uncertain. That uncertainty affects models of accretion, feedback, and halo pressure that shapes the disk's long-term evolution. We still do not know the origin of the highest energy cosmic rays, the particles that arrive with energies that strain known accelerators. Their arrival directions are smeared by magnetic fields, and their sources may be rare and transient, leaving little time-averaged evidence. If a nearby extreme event occurred in the past, its signature could be subtle and easy to misread. We also do not know which transient events have left fingerprints on Earth, despite the temptation of neat correlations. Isotopic anomalies, nitrate layers, and biological turnovers invite simple stories, but the causal chain is complex and often ambiguous. The honest conclusion is that the record is suggestive, not settled, and that uncertainty is part of the science. So the paradox resolves into a final map. Above and below are meaningful relative to the galactic plane and to the cosmic flow. They are filled with overlapping architectures that are radiative, magnetic, and gravitational, and each one shapes what can reach us. The CMB and its dipole give a universal backdrop and a motion vector that anchors large-scale orientation. The local bubble and halo give a nearby medium that filters messengers and stores history in plasma and dust. The heliosphere gives a moving boundary condition that turns cosmic weather into local exposure, and it does so with a rhythm set by the Sun. Gamma rays and gravity meet here, because both are maps of structure rather than mere points of light. Gamma rays trace where particles collide and where energy is injected, while gravity traces where mass must be, including mass that never shines. When we combine them, above and below stop being empty directions and become stacked columns with distinct properties. They become routes through which signals travel and through which we travel, carried by orbits and flows. The sky is not only a set of sources, it is a set of paths, and paths have conditions. The final answer is quiet because it is not a single object you can point to and name. Above and below the solar system are not voids, and they are not symmetrical emptiness. They are superposed backgrounds, particle seas, magnetic scaffolds, and gravitational basins that overlap without asking permission. And the ending is simpler than the map, even as the implications remain unsettling. The solar system is not a point in emptiness, and Earth is not sheltered by distance alone. It is a moving sensor carried through a layered universe, where the most dangerous light and the most silent mass arrive from directions once called up and down. Across this journey, above and below stopped being directions and became layers, measurable dynamic structures stacked around our solar system. We move from the galactic plane as a shared map, to the heliosphere's shifting boundary, to the local bubble's supernova-carved cavity and its possible chimneys venting toward the halo. Beyond that, we climbed into the Milky Way's vertical atmosphere, where magnetized plasma, cosmic rays, and hot circumgalactic gas blur the line between foreground and deep space. We watched high-energy messengers arrive, only to learn that their stories are edited by the path, scrambled by magnetic fields, absorbed by gas, and rewritten by diffuse gamma-ray glow. We followed the other thread as well, the one you cannot see at all, gravity's quiet current. Disk, bulge, bar, and a dark halo whose shape still refuses to sit still. The sun's orbit became a three-dimensional drift, a rosette through a potential well, bobbing above and below the midplane like a buoy in slow motion. That bobbing is not just choreography, it is an instrument. Each crossing, each vertical oscillation, encodes how much mass is really there and where it hides. Close to home, Voyager showed the heliopause is not a wall, but a weather front, porous and variable, where shielding breathes with the solar cycle and the interstellar wind. In the local bubble, Iron 60 and Earth's rocks hinted at nearby explosions, while dust shells and soft X-rays suggested a cavity still shaped by ancient shockwaves. Higher still, the thick disk and halo revealed an ecosystem of fountains and chimneys, where superbubbles punch through, metals circulate, and cosmic rays find highways or traps. Then the map widened again, past the Milky Way's edge into the local group Virgo and the cosmic web, where up and down become vectors in a flow field. Our motion gained a new reference frame in the CMB dipole, and our destination blurred into basins of attraction, the great Attractor's pull extending toward Shapley, beyond the zone of avoidance. And in every direction, regardless of structure, the backgrounds waited. The CMB's afterglow, the inferred neutrino sea, and the gravitational wave hush, reminding us that even emptiness has a temperature, and even silence has a spectrum. What we called space turned out to be architecture, and what we called nothing turned out to be a medium, full of filters, currents, and memory. So if space is empty, why does it feel like an unseen ocean, and what's really above us and below? Because above and below are not voids at all. They are stacked, invisible systems, plasma boundaries, bubble walls, halo layers, and gravitational basins, steering our motion and deciding what can reach us. The storm of particles and the silent drift were never contradictions. They were the same answer spoken in two languages, radiation and gravity, both shaped by the structures we move through. The unsettling twist is that a messenger from above is not automatically from beyond the galaxy, and a pull from below is not automatically nearby. Foreground and deep universe are braided together in the halo's haze. The real mystery is not that space is empty, it is that space is crowded with things we cannot see, until we learn how to listen, by tracing polarization, timing neutrinos, mapping gamma rays, and reading the sun's slow bobbing as a seismograph of dark mass. Somewhere in the chimneys of the local bubble, in the missing baryons of the circumgalactic medium, in the clumps and streams of the dark halo, and in the origin of the highest energy cosmic rays, the next revision of our map is already waiting. And when it arrives, it may not change what exists above and below us so much as change what we finally notice is already there. If you want to keep going, follow the next measurements: Gaia's growing kinematic atlas, new gamma ray and Cherenkov surveys, neutrino skies, and dark matter searches, because every improved map turns empty space into a readable place.